Are we live yet? Hold on, let me check. Should be live. Yep, we're live. Yes. We are live. Hello, guys. We are live, and we are live, and we are live. Today will be the reading of a preposterous book called Quantum Theory, with a new introduction by James Lees. Bohr, Einstein, Heisenberg, Planck, and Schrödinger. Okay. You know,
The viewers are gonna be so confused.
I'm also going. I'm also going to be checking chat. So yeah.
Are we live or something?
We are live. Yes, we are live.
Well, he is.
Hey. Then I'll just say hi. They can hear me.
Damn it! Hold on. The thumbnails.
What's wrong?
Thumbnail.
The thumbnail.
The thumbnail.
Okay. Yeah. Let me fix that real quick. MS Paint.
Quantum theory.
Quantum Theory reading. Part 1. And I'm just
Part
going.
1.
I'm going to be making a Christmas tree. Yeah, because I kind of want to.
Oh my god.
Oh my god, that's a bad Christmas tree. That's a beautiful Christmas tree. And I'm gonna sprinkle red and green all over it. And yellow. Why not? The reading will start momentarily.
My cat is petting me.
What? Huh?
My cat was petting me.
I think it's supposed to be the other way around.
My cat has become intelligent.
Okay,
It's so
save.
intelligent it even knows it has solved most of my homework.
QTRP 1. Quantum Theory Reading Part 1. Let me just change the what is it called? Thumbnails. And then Q. Okay, there we go.
Oh, Atlas joined.
Oh. Who joined?
Who's watching this?
That's one of my other friends that just joined the realm. Well, the world.
Oh, can I have operator?
I guess.
Alright, if you want to come down to the campsite.
I don't think Alice is watching your stream.
Okay. Okay.
Oh my god, big RV, big RV.
Okay, can you come down here, please?
I'm playing with an RV.
Yeah. I see you over there, Jay. I see your name tag at least. Why does this chair
I
have
wonder
like 2
who's
health?
watching the stream.
Yeah. Okay.
Did I?
I said one word in the stream and that was.
Hey Siri, set a timer for 5 minutes.
5 minutes.
We will start the reading in 5 minutes. I'm
minutes.
also going to be checking chat, and this is gonna go on for like the entire day probably. I want to see how much we get done today. I kind of want to get back to where I am. Oh, I thought that said Shrek.
We're gonna hold eyes on the stream. I wonder who will watch the stream.
Yeah.
I said one word in the stream just to welcome people when they first join is E.
I also might have to use Quantum Paint. I mean Microsoft Paint.
Quantum Paint is crazy.
Microsoft Paint to show you some of the equations in this book. So
I'm gonna go back
actually
to YouTube real quick.
Minecraft. I might have to use animation desk for this. Because that's where I used to draw.
My cat is sleeping.
Okay, hopefully that works. Create new scene. Window capture 12. Yes. There we go. Minecraft and scene 2.
I'm just.
Okay. I'm back in Minecraft, guys. Oh, hey Jay. Let me get back into my original seat. Oh,
This is
your
fine.
chair's dying. Your chair's dying. Your
The
chair's
chair,
dying.
no.
No.
The chair's
End its
dying.
misery.
Yes. I mean, no.
Okay. 2 viewers. Share the stream to everybody you know who likes quantum theory. I am going to be bringing my mic closer to my face, and also do not judge me for my reading. And also, I am sick today. Just to let you know.
That's not very good.
I guess both me and corrupted are sick, I guess.
And also, I might have to go down to eat lunch soon. It's already like 3:45. I usually eat lunch at 4.
Yeah, the barrier will stop the chairs from going onto the thing.
Yes.
How many people are watching the stream? Still
2 right now, yeah.
I wonder who's
Hi.
watching.
My chair has 2 health. Okay, anyways.
Chair has 2 health.
F1ing. We have 1 minute, 2 minutes on the clock.
Two minutes left. So people just start talking about random stuff.
Also, guys, you can see in chat as well. You could type in chat, and I'll be responding to people. So yeah, social.
Hold on, so send me a stream link so I can actually look at the chat and read it.
I might add you as a stream monitor actually, Jay.
Ah yes, reading quantum theory part 1. The Merry Christmas.
It's really something.
I hate the new Discord interface on mobile.
Then we can be 2. I also hate it.
$50 seconds.
Someone joined and I want to know who. Do you like tacos with ketchup?
I believe it's Atlas.
Hello.
Oh, welcome.
Yes.
Welcome.
Okay. I'm going to start reading in 30 seconds. So if you want to watch this,
Oh, you just
Okay.
have your thing in F1 mode.
Yeah. Yeah, I do.
It's kind of good to be featured in a stream.
Mhm. Also, go sub to these people
For the
that joined
first
the
time.
stream. Jay Snar, Blackouts Gamer, and I don't know if this guy has a channel.
Atlas don't have a channel.
Okay. Well,
I don't know how
anyways,
to work Discord servers, so
7 seconds until I start reading. Yep, you heard it.
Reading time.
Yeah. Okay, quantum theory. Let us read the side first. Great works that shape our world. Bohr, Einstein, Heisenberg, Planck, and Schrödinger. Quantum theory, with a new introduction by James Lees. Flame tree. Bohr, Einstein, Heisenberg, Planck, and Schrödinger. Quantum theory, with a new introduction by James Lees. Great works that shape our world. Then the back. The breakthrough discoveries in quantum theory by the physicist featured here led directly to computers, smartphones, and MRI scans. A definitive new series bringing together ancient, medieval, and modern texts, each with an extended introduction highlighting the special contribution of each book. Great works that shape our world. Opening up the book. 1 blank page. 2 blank page. 3 blank page. Great works that
What's
shape
the way
our
blank
world.
page?
Niels Bohr, Albert Einstein, Werner Heisenberg, Max Planck, and Erwin Schrödinger. Quantum theory. This is a Flame Tree book. Flame Tree Publishing, 6 Melbury News, Fulham, London, SW6 3NS, United Kingdom. www.flametreepublishing.com. This expanded edition first published in copyright 2022. Flame Tree Publishing Ltd. Publisher's note. Our series aims to reproduce for the modern reader of works of great cultural, scientific, and historical significance as they were published originally. To this end, you may notice there are some inconsistencies in the quality of images and styles of the equations as they derive from... I don't know that word. Of the original editions. This edition is based on the original publication of Bohr's On the Quantum Theory of Line Spectra, 1918, Andrew Fred, Holst and Son, Copenhagen. The translation of Planck's The Origin and Development of Quantum Theory, 1922, by H.T. Clarke and L. Silberstein, Clarendon Press, Oxford. The translation of Einstein's On a Heuristic Point of View about the Creation and Conversion of Light, by Wikisource, Creative Commons Attribution, Share Alike 3.0, unported. Originally published in German in the Annalen der Physik Scientific Journal in 1905, the translation of second edition of Schrödinger's collected papers on wave mechanics, 1928, J. M. Shearer and W. M. Deans, Blackie and Son Limited, London and Glasgow, N.B. Les several later papers thereof, and the translation of Heisenberg's The Physical Principles of Quantum Theory, 1930, by Karl Eckart and Frank C. Hoyt, the University of Chicago. Lists the appendix. 22, 24, 26, 25, 23, 1, 3, 5, 7, 9, 10, 8, 6, 4, 2. ISBN 978-1-83964-999-8. All rights reserved. No parts of this publication may be reproduced, stored in a retrieval system, or transmitted in any form or by any means, electronic, mechanical, photocopying, recording, or otherwise, without the prior written permission of the publisher. Cover and pattern art was created by Flame Tree Studio. A copy of the CIP data for this book is available from the British Library. Designed and created in the UK, printed and bound in China. Of course it's China. Great works that shape our world. Niels Bohr, Albert Einstein, Werner Heisenberg, Max Planck, and Erwin Schrödinger. Quantum Theory. With the new introduction by James Lees. Great works that shape our world. Flame Tree Publishing. Contents. Quantum Theory. Contents. A new introduction to Max Planck and Niels Bohr by James Lees. 10. Max Planck, New Horizons in Science. 10. Niels Bohr, Quantum Theory and the Atom. Page 20. Modern Perceptions. Page 28. A new introduction for this edition to Albert Einstein, Erwin Schrödinger, and Werner Heisenberg. Page 36. 10,000 Great Works. Page 36. Albert Einstein, On a Heuristic Point of View Concerning the Production and Transformation of Light. Page 36. Erwin Schrödinger, Collected Papers on Wave Mechanics. 38. Werner Heisenberg, The Physical Principles of the Quantum Theory. Page 40. On Reading a Scientific Paper. Page 42. The Origin and Development of the Quantum Theory by Max Planck. 45. Notes. Page 58. On the Quantum Theory of Line Spectra by Niels Bohr. 63. Introduction. 64. Publisher's Note. 66. Part 1. On the General Theory. General Principles. 67. Systems of 1 degree and freedoms. 73. Conditionally Periodic Systems. 83. Part 2. On the Hydrogen Spectrum. Page 111. The Simple Theory of the Series Spectrum of Hydrogen. Page 111. Number 2. The Stationary States of Perturbed Periodic System. Page 117. Number 3. The Fine Structure of the Hydrogen Lines. Page 146. 4. The Effect of External Electric Field on the Hydrogen Lines. Page 155. 5. The Effect of a Magnetic Field on the Hydrogen Spectrum. Page 169. Nice. Number 6. The Continuous Hydrogen Spectrum. Page 194. On a Heuristic Point of View about the Creation and Conversion of Light by Albert Einstein. Page 199. A Certain Problem Concerning the Theory of Black Body Radiation. Page 201. Planck's derivation of fundamental quantum, page 203. The entropy of radiation, page 205. Limiting law for the entropy of monochromatic radiation at a low radiation density, page 207. Molecular theoretical investigation of the volume dependence of the entropy of gases and dilute solutions, page 208. Interpretation of the volume dependence of the entropy of monochromatic radiation using Boltzmann's principle, page 211. Stokes rule, 212. On the generation of cathode rays by illumination of solid bodies, on page 213. Ionization of gases.
Well, we're already on page 213. What?
No, we're at page 6. Page 213.
Oh.
Ionization of gases by ultraviolet light, page 216. I'm just reading the contents. Collected papers
I
on
don't think
laser
anyone.
channel-
You're reading the contents.
Too bad. Preface to the first German edition, 220. Abstract, 221. Quantization as a proper problem of proper values, part 1. Quantization as a proper problem of proper values, part 2. 242. The Hamiltonian analogy between mechanics and optics, page 242. Geometrical and undulatory
It was killed by
mechanics.
intentional gay design. When did Bedrock have Java death messages? What the hell?
What?
Okay, so I found something. I accidentally right-clicked on it and it blew up.
Okay. Anyways, abstract 221. Quantization as a problem. Okay, I already did that.
Well, but when did Bedrock Edition have Java kill death messages?
I don't know.
Okay, I accidentally blew up one of your things.
Why'd you blow up one of the runes?
No, it wasn't a room. It was in the middle. It was in the middle of a
Okay.
fucking river.
Can I read?
I accidentally clicked it. I didn't know what. I expected it to blow up.
Can I read now?
I never used respawn anchors. Okay.
Application of examples, page 262. The Planck oscillator, the question of degeneracy, page 262. Rotator with fixed axis, page 267. Rigid rotator with free axis, 268. Non-rigid rotator diatomic molecule, 270. The continuous transition from micro to macro mechanics, page 276. On the relation between the quantum mechanics of Heisenberg, Born, Jordan, and that of Schrödinger. Wait, are they referring to Michael Jordan? Page 281. Introduction and abstract, 281. The coordination of an operator and of a matrix with a well-arranged function symbol and the establishment of the product rule, 283. Heisenberg's quantum condition and the rules for partial differentiation. I almost read defenestration. Page 287. The solution of Heisenberg's equations of motion, 290. Comparison of the two theories, prospect of a classical understanding of the intensity and polarization of the emitted radiation, 297. Quantization as a problem of proper values, part 3, 303. Perturbation theory and with application to the Stark effect of Balmer lines, 303. Balmer lines, not bomber. Introduction, abstract, 303. Perturbation theory, 306. A single independent variable, 306. Several independent variables, partial differential equation, 312. Application to the Stark effect, 322. Calculation of frequencies by the method which corresponds to that of Epstein, 322. Treatment of the Stark effect by method which corresponds to that of Bohr, 343. Mathematical appendix, 349. The generalized Laguerre polynomials and orthogonal functions, I think, 349. Define integrals of products of two Laguerre logs or orthogonal functions, 351. Integrals with Legendre function. What? Okay, I can't read like half of those words on the bottom page of 7. Anyways, quantization as a problem proper values, part 4, 356. Also, hello Blackouts, you should go sub to him. Eliminations of the energy parameter from the vibration equation, the real wave equation, non-conservative systems, 356. Extension of the perturbation theory.
Wait. How long is this book?
Let's see. It's like 479 pages long. I'm gonna have way too many parts to this. Okay. Where was I? Quantization as a problem of
Just-
proper values, part 4. No, I'm reading.
Just read
the,
100.
No,
Read
I'm,
100. Read 104 pages at each part.
I'm reading the entire book. Every single piece of ink, ever. Eliminations of the.
Well, then we're gonna be here for 5 years.
Yeah, energy parameter from the vibration equation, the real wave equation, non-conservative systems, 356. Extension of the perturbation theory to perturbations containing the time explicitity, time theory of dispersion, 359. Supplements to excited atoms, degenerate systems, continuous spectrum, 367. Discussion of the Renaissance case, 374. Generalization of an arbitrary perturbation, 376. Relativistic magnetic generalization of the fundamental equations, 378. I cannot speak right now. On the physical significance of the field scalar, 380. The physical principles of the quantum theory by Werner Heisenberg, 387. Forward to the English edition, 388. Chapter 1, Introductory, 390. Theory and Experiment, 390. The Fundamental Concepts of Quantum Theory, 392. Chapter 2, Critique of the Physical Concepts at the Corpuscular Theory of Matter, 399. The Uncertainty Relations, 399. Illustrations of the Uncertainty Relations, 404. Chapter 3, Critique of the Physical Concepts of the Wave Theory, 427. The Uncertainty Relations for Waves, 427. Discussion of an actual measurement of the electromagnetic field, 431. Chapter 4, the statistical interpretation of quantum theory, mathematical considerations, 433, both of them. Interface of probabilities, 436. Bohr's concept of complementary, 438. Chapter 5, discussion of important experiments, 442. Diffraction experiments, 450. The experiment of Einstein and Rupp, 452. Emission, absorption, and dispersion of radiation, 453. Interference and the conservation laws, 459. The Compton effect and the experiment of Compton and Simon, 462. Radiation fluctuation phenomena, 465. Relativistic formula of the quantum theory, 470. Biographies, 474. Okay, we have gotten through 9 pages already. Nice.
That's a whole lot of pages.
Mm-hmm. A new introduction to Max Planck and Niels Bohr. Max Planck, A New Horizons in Science. In 1894, at the dedication of the University of Chicago's Ryerson Physical Laboratory, Albert Michelson, for 1852 to 1931, one of the foremost physicists of the time and discoverer of the speed of light, observed that while it is never safe to affirm that the future of physical science has no marvels in store even more astonishing than those of the past, it seems probable that most of the grand underlying principles that have been firmly established, and that further advances are to be sought chiefly in the rigorous application of these principles to all the phenomena which come under our notice. It is here that the science of measurement shows its importance, where quantitative work is more to be desired than qualitative work. An eminent physicist remarked that the future truths of physical science are to be looked for in the 6th place of decimals. The language may be elaborate, but the message is clear. Physics is just about done. We have discovered all the big things, and now it is just a case of working out the finer details. Admittedly, a rather downbeat note to open a new laboratory, however you pronounce it. Yet such a sentiment could not have been further from the truth. Michelson's own famously unsuccessful experiment to discover the luminous ether just 6 years earlier was to pave the way for the discovery of relativity in 1905 by Albert Einstein, 1879 to 1955. Even before that, in 1900s, Max Planck, 1858 to 1947, with the help of his successors such as Niels Bohr, 1885 to 1963, was going to turn physics on its head. Beginning the quantum world. The importance of quantum theory to our understanding of the world is something to which we will return. It simply cannot be understated. Quantum theory is a foundation of so much of our understanding of how and why the universe works. Some of our technologies today, and many of those that will develop in the future, are rooted in some kind of quantum phenomena. Without our understanding of its complexities, the world that we inhabit would be fundamentally different. The difficulty for anyone who chooses to dive into a world full of quantum is that you must first leave what you think you understand by the wayside. Quantum is an existence based in statistics. To explore it, you need to appreciate that things can, and often do, defy the laws of logic and common sense. Even practicing physicists can struggle to comprehend fully or even believe their own findings. But the maths and experimental evidence are there and cannot, as much as some might wish, be denied. It is for this reason that Max Planck's scientific work is so important. It was he who first took the leap into the illogical, presenting his findings and ideas that solved problems and were supported by the facts, even if they did not make intuitive sense. It was he who managed to get the first crucial foot in the door, which allowed generations of scientists after him to follow and make sense of the strange quantum world. Planck's deceptively complex idea was to limit the possibilities of energy seemingly arbitrarily, and thus reduce them down to the so-called quantum of action, which this was to be the first step in a process that would form the modern idea and understanding of quantum theory. Niels Bohr was another key player in our understanding of quantum physics. He was not the first to try and explain the inner workings of an atom, but he did make the first leap into combining such workings with quantum theory. This was still a new concept, but one that, thanks to Einstein's solving of the photoelectric effect in 1905, was now widely accepted. Many scientists began to dabble. The depths of understanding how fundamental a change in thinking it was, and the strange consequences to be explored later by Werner Heisenberg's 1901 to 76 and Erwin Schrödinger 1887 to 1961 were not yet uncovered. However, the work they had begun, and one of the first great achievements for quantum theory, would come in the building blocks of all things. End of page 13. I'm going to take a sip of water real quick. How are you guys doing?
Yes.
My answer
Apparently,
is
Michael
good.
does not. Apparently, Michael does not have a toothbrush somehow.
Seriously?
Yeah, he's locked in his room.
How's he? Why is he?
Did you
locked
guys
in
not
his
know
room?
that?
I knew that. but,
Because
like,
of his
why is
psycho
he-
mother.
Why is he locked in his room?
You locked in his room?
Yeah. He's locked in his room because of his mom.
Damn.
She doesn't let him go out. So that's why I have plans on, if I did, I would walk all the way to his country to pick him up.
That sounds like fucking child abuse. The hell?
It is.
It
That's
is,
why
yeah.
me and friend were in VC the other day talking about why we're so mad at his mother right now. And I want to pick him up, and the same for Fran.
Wait, no, that was
Okay.
page 11. Okay.
It's going
Should I
called
continue?
Child Protective Services.
Should I continue?
Yes.
Okay.
D.
D. You said C.
C is yes in Spanish.
I know. Okay.
Do you know what no is in Spanish?
9. That's German.
No. No.
Okay. Anyways, the atom. The idea of a fundamental component of the universe has been theorized as far back as the ancient Greeks, who gave us the name atomos, meaning unable to cut/divide. Yet, it was not until 1803 that John Dalton, 1766 to 1844, posed that the idea that there was a set of atoms that formed the building blocks of matter. Combinations of those atoms made everything in existence. Dmitry Mendeleev, 1834 to 1907, then started to construct a list of the fundamental atoms, building the periodic table that is now used across the world. The introduction of this atomic theory helped to move chemistry forward by leaps and bounds. A greater understanding of the fundamental components enabled scientists to make better predictions about what chemicals would combine and what they could do. It was even possible to predict the properties of elements yet to be discovered. In physics, the discovery and uses of radiation in the form of alpha, beta, gamma, and X-rays were explored at the higher ends of the periodic table. But even as the theory of the atom was widely accepted and employed across all sorts of science, what actually looked like remained a mystery. Countless scientists have spent the time trying to figure out what made an atom tick. George Johnstone Stoney, 1820. Ooh, Beluga Rhino is playing Marble Snap.
Marvel Snap.
Yeah. George Johnstone Stoney trying to figure out.
Johnstone Stoney?
Yes.
What?
That's actually a name, yeah. George Johnstone
Wait,
Stoney.
what?
Yeah, it's a name.
That's a name.
1826 to 1911, coined the term electron as a fundamental unit of electricity, and J.J. Thomson, 1856 to 1940, worked out that these electrons were truly tiny. Ernest, just like you, Ernest Rutherford, 1871 to 1937, then discovered that alpha radiation was emitted from the atom and calculated that the mass of an atom must be concentrated in a central nucleus. Bohr's insight was that the experimental results could only truly be explained through the lens of newly emerging discrete integer states of quantum theory. These alone allowed for the creation of a model that fitted all of the experimental evidence available. It is hard to overstate the importance of properly understanding how an atom works. The ability to describe properly the fundamental building blocks on all which matter is built is crucial to almost everything. Every area of science and engineering, from our understanding of how stars burn to how to build tiny transistors that power a modern electronic world, is informed in some way by our knowledge of the atom. Both Planck and Bohr drew upon quantum theory to expand scientific horizons. They both directly contributed to solving some of the big questions there were in physics. In doing so, they not only found solutions to the problems, but also created scientific ideas and techniques for examining. Hold on, I gotta unlock my phone. Examining a much broader section of the universe than they could possibly have hoped for. Planck's quantum theory was to open up the scientific world to a brand new horizon. Alright, end of that section. What do you guys think?
I've just been listening while mute, and I can say it's perfect.
Yes.
Down to the last.
Not really. I messed up so many times. Anyways. Planck and the ultraviolet catastrophe. Max Planck was born in 1858 to a family of intellectuals in what is now Germany. By the age of 22, he had completed his higher education, earning both a doctoral degree and a habilitation. During his studies, he was told by one of his professors, Philip von Jolly, ho ho ho, Merry Christmas, 1809 to 84, that in physics almost everything is completely discovered. All that remains is to fill a few unimportant holes. Seemingly undeterred by this dismissal of his chosen profession, Planck worked his way to a professorship at the University of Berlin, studying thermodynamics and applied physical chemistry. It was at Berlin that he was approached in 1894 by a number of electrical companies seeking to improve the efficiency of light bulbs. In working on this, Planck encountered a long-standing problem in physics: the ultraviolet catastrophe.
Physics.
Hold on, I'm gonna be right back.
It's pretty quiet.
I can change that.
Jesus Christ.
Okay,
Didn't have to
I
give
am
me
back.
500 heart attacks.
Okay, after this one.
Michael's being a bully.
Oh, how?
He's not being a bully. He's
he's-
locked in his room. Maybe that's why.
He's being a menace to society.
I'm already a mess in society.
Whoa. What is he talking about?
I was talking to him, and then after I was done talking to him, I said, "Who wants to know what no is in Spanish?" And he said, a German, the German version of no, and I said, "No, that's German." He said, "Are you fucking stupid?"
Okay, anyways.
Right?
A black body is an imaginary physical construct.
The black body, what?
It is an object that absorbs all of the electromagnetic radiation, light, radio, infrared, ultraviolet, etc. etc. How dare you?
What? Jingle bells.
Okay. Can you stop playing it, please?
Well, we can't have any Christmas music while we're reading Quantum Theory.
Fine, get the music bot in here and just put some non-copyright Christmas music in the background, not too loud, alright?
Jingle bells is literally not even copyrighted.
I know, just like put it.
We can do that.
Put an instrumental
do
part
that.
of. Put an instrumental version of Jingle Bells in the background. Like using like the music bot or something, I don't know.
I need to get a YouTube link real quick.
Alright. If such an object were to exist, it must
There's
also be
four
able to
people in a
emit all that
VC.
energy again with 100%
Doing
efficiency.
a stream.
Think of it as something that, when heated, emits light. Metal, for example, glows when really hot. Exactly.
No, really?
No, that's what the book says. Exactly what kind
That's
of
what
light.
the book says. The book's speaking stuff that we already know.
The object emits depends on
Where
how
can I
hot
find
it
this
gets.
book?
The problem is that according to the then known laws of electromagnetism, that's literally all one word. The spacing's so awkward. The outputted power of a black body would be infinite. Even if you tried to apply the equations to the less than ideal real-world objects, such as a star or even a simple light bulb, you would find that it would be producing enormous quantities of ultraviolet light. It was clear to see from experimentation that this simply was not happening. Something was wrong with the equations. The need for a solution was not considered pressing, but the question was a constant thorn in the side of physics. It remained outgoing for some 50 years, during which time thermodynamics has become an increasingly important field of study with wide-reaching practical applications. As such, a sustained effort was made during that period to scrutinize the problem. Max Planck was not, as you might imagine, the first person to try to solve the issue. Another physicist, Wilhelm Wien, 1864 to 1928, had found a partial solution in 1896. It worked well for short wavelengths, but became functionally useless as they grew longer. Plenty of other scientists also attempted to solve the problem, but nothing they did seemed to work. Okay, I'm actually gonna eat lunch real quick, because I haven't eaten lunch since yesterday. Just remind me I'm on the Planck solution. Alright, see you guys in a bit. Please do not, actually I'm gonna deafen on Discord. Okay, I will see you guys in a bit.
Does Michael really not know what touche means?
Hey, I'm back, by the way.
Oh, he's
Compare-
back.
Apparently, Michael Mel does not know what touche means.
Seriously? Touche.
Touche.
Oh yeah, I know. I brought some cheese upstairs.
Jeez.
Yeah.
I have an entire meal right now.
I'm warming up some pizza pockets. Okay,
I'm just.
let's go back. Let's get back to reading. The Planck solution.
While Jigables is playing in the background.
In previous attempts to find a solution, Planck had created his own hybrid Wien-Planck law. However, the evidence failed to support his conclusions. So there's another chair dying. So he returned to the drawing board. He was the most experienced in the field of thermodynamics, how heat works, and entropy. So it was here that he focused his efforts. Time and time again, however, his understanding of physics, more specifically the second law of thermodynamics, which states that entropy is an isolated system, always increases, proved sufficient. It was in these efforts that Planck came to examine the work of Ludwig Boltzmann. Boltzmann had undertaken studies in entropy, a measure of the amount disorder in system, best likened to taking a cup of water and adding in some dye. At the start of the system, it is relatively ordered, in which most of the water and dye being separate. Over time, as the fluids mix, the system becomes increasingly chaotic. In these conditions, it is virtually impossible to describe properly where each individual possible particle of dye and water is located. This concept was well understood, but Boltzmann had a new idea. Assuming that all of the different atoms can move freely and randomly, then what was to stop the two from spontaneously unmixing and ending up with dye floating on top of the water? Nothing. In short, yet the chance of this happening is minuscule. The chance that all of the individual particles would just coincidentally separate is infinitesimally small. Infinitesimally
The way that
small.
the way
Just
the
like you.
person did the what?
The chance that all of the individual particles would just coincidentally separate is infinitesimally small, just like you. To any practical purpose is completely nil. This
Was the just like you the part of the book, or
No,
like did you
no.
just say that?
no.
How?
It was toward you.
Wait, how am I small? Huh? I'm confused.
Tiny boy. This was approaching the law of physics in a statistical way rather than more traditional deterministic route of strict actions and consequences. Planck was skeptical of this approach, but in self-confessed act of desperation, he set to work. In 1900... What? Oh, huh? What?
Oh, floating chair.
In 1900, Max Planck presented a new idea to a meeting of the Deutsche Physikalische Gesellschaft, German physical society. It took the
The
form
hell's
of...
like a shell shaft?
It's German. It took the form of a simple equation, Planck's postulate. E equals hv. The postulate states that energy, E, is equal to some
Ooh, big
multiple
word. Postulate.
of the frequency V multiplied by the Planck constant, h. Yes.
H.
H.
As the British say.
H. Yeah.
And me sometimes.
Me too. I say H sometimes. Do you guys ever eat the skin of a cheese?
The skin of it. What? Huh?
There's skin on my cheese.
I don't think that's normal for cheese.
Oh, okay. I'm gonna check if my pizza pockets are done. Next section is the meaning of Planck's postulate.
Can I have a cheese pocket thingy?
Mm-hmm. Yes, you can. Be right back.
Yeah.
Okay. Hello, guys. I am back and in my chair. Okay.
I think Corrupted's back.
I literally just said that. Thankfully, I saved some utensils from my school. That doesn't make any sense.
Yes.
Cool. Cool school. School not cool. Cool school. School cool. Cool school.
My school's cool.
School. Crunchy.
Crunch. You want some, Jay?
Yes.
Ah. How many viewers we got? Send this to everybody you know.
One, which is me.
Send this to everybody. Oh. Someone just texted me. I'm taking a little break to eat lunch real quick.
Num num num.
Oh, Dog of Wisdom. I should not be wearing a fancy uniform.
You're still wearing your uniform?
Mm-hmm. Actually, hold up. I'm gonna change out of it real quick. I'm gonna mute.
I just like this song. Glock 19, so Jay doesn't like correct me with Glock 19.
Glork.
Glock 19.
Glork 19.
Directed by Jay Small.
Huh?
We're talking about Glork.
Glock 19, the movie, directed by Jay Small.
Okay, I'm back in my casual outfit.
Casual outfit. I'm in my long shirt.
Yum. Yum
Just
lunch.
in my kitchen. I am in
Hey.
my kitchen, my natural habitat,
Oh.
where I want to cook something
Okay.
alive.
Beluga Rhino is playing Marvel Snap.
How long are you gonna be play? How long are you gonna be Marvel snapping for?
I wonder if he'll rejoin this VC at some point just randomly.
He's going to. I guarantee it.
Who?
Jay, where
I
are
just
you?
bet now that I've said that he might join, he will join.
Anyways, continuing. Planck and the ultraviolet catastrophe. Max Planck was born in 1858 to a family of... Oh, I already read that. When did the page turn? Okay, the meaning of Planck's postulate. The effect of such short and apparently simple equation is enormous. It carries the implication that all energy from a source must come in discrete units. That is to say, the energy of light coming from a light bulb can only be, for instance, 100 joules, 200 joules, 300 joules, etc. Crucially, it could not be 150 joules, 237 joules, or any number that fails to fit the rule. With that simple statement, Planck created the quantum theory and established two fundamental tenets. The first is that quantum acts on a very, very small scale. The value of Planck constant h is 6.63 times 10 to the negative 34 joule dot seconds, 0.0 zero 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 0.00000000000000663. So the difference in energy levels is tiny. It is so small that in practicality the energy states are measured in electron volts, the energy of just a single electron under 1 volt. This small scale then extends to almost all quantum effects. They happen on incredibly small scales so that the effects were previously unnoticed. The second tenet of quantum is that it is inherently statistical. In order to get this quantized energy to work, Planck had no choice but to apply it statistically to get the right answer. The classical approach to all of physics was a deterministic one. If you hit a snooker ball the same way 1,000 times, then the resulting movement will also be exactly the same. In a statistical system, however, there's a small chance of a different outcome even if the setup and movement are exactly the same. No, you're not. Just the reading.
Oh wait, failure joined.
Who? The failure?
Welcome.
Oh. Are you just preventing the chairs from dying?
Yes.
Okay.
What did the chairs do?
Okay. A quantum of action. Prior to Planck's theory, all of the widely accepted physics has viewed energy as a continuum, a number line from which any value could be chosen. Even Boltzmann himself, the originator of the considering problems in a statistical way, would convert his answers back to a continuum by assuming that the individual bits of energy were so small as to be nothing at all. Planck was not happy with this, however, although he wished dearly that he could simply convert back to the continuum, he found that his theories did not allow it. The value of these amounts of energy is so-called quantum of action came out time again and again with the value of h. This certainly represented an incredibly small number, a number so small that even today it is often considered one of the smallest numbers of any real meaning, but it was not small enough to be ignored. The physical meaning of h was not clear, but its use quickly became obvious. It allowed the solving of many great issues, of a great many issues, not only with the problem at hand, but in other related areas. Planck saw h only as a stopgap, however, something that further exploration would explain and eventually replace. Nowadays, h is a piece of physics that shows up in almost every single equation based on quantum mechanics. It provides the foundation of not only quantum mechanics, but also, following a redefinition in 2019, of a fundamental universal unit used to define a kilogram, and by extension, all weight. I definitely understood that. Did you guys understand that?
Totally.
Nope.
Yeah, totally.
I was the only one who said nope.
It's
Okay.
so mean, Blackout.
Solving the black body problem. The solution to ultraviolet catastrophe was, of course, a little harder than a simple equation such as Planck's postulate, brilliant as this was. Drawing on this newly formulated idea of the quantum of action, Planck was able to apply this along with more classical knowledge into the rather more complicated spectral distribution function. And I'm gonna have to draw this one out. As I read each section that has one or more equations, I will just write the equations in that section. So in this case,
Time to drawing.
it'll be B, whatever this is,
What is corrupted gonna draw? B. I don't understand that letter.
I can't. Divided by. I don't even know what this means.
Just don't look at the chat.
I won't. I'm not looking at anything. In this formula, whatever that letter is the wavelength of the light. T is the temperature, H is Planck's constant. Okay, so this letter right here is the speed of light, or wavelength of the light. T is temperature, H is Planck's constant, and C is the speed of light, and KB is a Boltzmann constant. This is what actually solved the problem. Using Planck's equation, it's now possible to take any object to produce an accurate idea after taking measurements of its temperature and wavelength of how much power it could output. Planck's work had been done surely to the delight of his industrial sponsors, yet the equation would not only work on the scale of light bulbs that he had been considering, it could also be expanded all the way up to the bright light of stars. The equation in Planck's publication really remains largely unchanged today, apart from some minor variation due to changing convention on best way to write an equation. I totally understood that. The reluctant revolutionary. The presentation and subsequent publication of Planck's postulate resulted in a monumental shift in physics. His discovery shook the foundations of physics. It proved an equation so powerful that it could shape an entire epoch of science and touch nearly every scientific endeavor that succeeded it. Despite this, the scientific community, including Planck himself, were initially rather nonplussed with the work. Despite having become the father of quantum physics, although his postulate, Planck remained unsatisfied with it. To him, the quantization of energy was merely a means to an end, a mathematical trick that neatly solved the problem, but provided no insight into the physics behind it. This was also for a while opinion of many of his peers. A solution had been found and everybody was pleased, but then they returned to whatever it was they were doing. To Planck and many others, the resulting conclusions of quantized energy and statistical distributions flew in the face of everything in physics that was thought to be known. His work was not attacked or shunned, but seemed mostly to be considered as a work in progress. Planck spent several following years trying to match the classical ideas of physics with his quantized energies and the evidence before him, leading him to be dubbed the reluctant revolutionary. Nice history. So basically the equation was not enough. Blackout gamer. Kuru. Okay. That was actually really interesting. What do you think of the book so far?
Very long.
Yeah.
Okay. How'd you say? 17 pages out of 479. Or 400.
Well, considering that we started at like a while ago and it's 5:50 now.
Okay. A rising tide of recognition. While the scientific community may have been slow on the uptake, which with many hesitant over the wider ramifications of Planck's discovery, it was duly accepted and praised by most. Younger physicists, in particular those not too set in their ways of thinking, immediately began working with the so-called quanta of action. They applied it to problems across the whole spectrum of physics and sought to explore the strange new world to which Planck had opened to the door. Planck was one of the most recognized and acclaimed physicists of his day. His honors were numerous and deserved. In 1918, he was awarded the highest honor any scientist could hope to receive, a Nobel Prize. The citation acknowledged that the award was made for the services he rendered to the advancements of physics by his discovery of energy quanta. Already a fully fledged professor by the time of his discovery, Planck retained his academic post in Berlin, but also assumed increasingly important scientific roles. Thanks to both his high-profile discovery and hardworking nature, he became the president of the Kaiser Wilhelm Society, later changed to the Max Planck Society, and the permanent secretary of mathematics and physics for the Prussian Academy of Sciences. Planck had also become the de facto head of physics in Germany. Even after his death, Planck's contributions to science were celebrated. Countless buildings, institutes, and statues, and even Germany's High Medal of Honor for the study of physics were dedicated to him, ensuring that his achievements in quantum physics would not be forgotten. End of that section. I'm going to return the cheese now. Whenever I try to open up Discord, I actually open up Osu.
See you next time.
How?
But anyways, I'm gonna return the cheese back to the refrigerator. Okay, I'm back. I am dead from back. I am dead from the back.
Oh, hi. Oh, please, Minx, I don't want to hear Iris again.
Huh?
I won't ship you and Michael. Please just don't bring Iris here.
How do you say the name?
Hugra?
I don't know.
Hugra?
Yeah.
Yeah.
I don't know who changed my name to that.
Okay. Okay, continuing quantum theory. I need water, hold on. Need a refresh. Okay. Jesus Griffin. Okay. Which one did I just read? Rising Tide of Recognition? Yeah. The photoelectric effect. The first widespread moment of recognition for Planck's theory of the quantization of energy came with the solving one of the era's great physics questions. Why does light need to be below a certain wavelength in order to cause metals to release electrons? The answer is so-called photoelectric effect. To understand fully why this is such a big deal and how it was a direct consequence of Planck's work, we must first understand what the photoelectric effect is. It could be described as the process in which a piece of metal can be made to emit electrons when a light is directed upon it. This was discovered by hooking such a piece of metal to an electric circuit. When light shone upon it, a buzzer or electronic device, such as a buzzer or a light, started working. The problem was, however, that experiments showed the frequency of the light, which in this case corresponds to the color of the light, to be important. Below a certain frequency, the metal would no longer produce the electrons. According to the classical theories, such a result did not make sense. The light gave electrons away energy in which to escape the metal. If the frequency is lower, then the process would simply take a little bit longer to get underway. Einstein's solution. In 1905, the 26-year-old Albert Einstein had his annus mirabilis, Latin for wonderful year. Yes. In just this 1 year, he released 4 groundbreaking papers, each of which revolutionized an aspect of physics. One of them was rooted in Planck's theory of quantized energy, the photoelectric effect. Einstein's paper was entitled Über einen die Zugang und Verwandlung des Lichtes betreffenden heuristischen Gesichtspunkt. On a heuristic viewpoint concerning the production and transformation of light, it sets out a solution to the photoelectric effect that directly took Planck's idea and put it in a practical way. To solve the problem, Einstein took the quantization of energy one step further. He proposed that light travels as photons, wave packets of energy that act like particles. Light thus delivers all of its energy in a single burst, meaning if the frequency and thus the energy of a photon is not high enough, the electron will not be able to get free. This is the moment that quantum theory really sunk in. It not only cemented Einstein's place as one of the greatest physicists ever, but also pushed Planck's work into the limelight and gave it the wide recognition it deserved. So significant was this push that some even consider it to be the true birth of quantum physics, although most will agree it was Planck who had the original idea. Clearly, there was no ill will, as Planck promoted Einstein into the academic system and acted as a mentor for the rest of his life. Planck's further work. While, not surprisingly, none of Planck's other scientific work came close to the achievement of founding a new era of scientific discovery, he remained highly active. He continued to contribute to a number of areas, such as his beloved thermodynamics, his reluctant bedfellow of statistical mechanics, and other fields such as optics and physical chemistry. Hold on. Where was I? Even after his retirement, Planck continued to pen letters and papers on philosophical and theological matters. Key among the topics he discussed was his vehement opposition to the statistical understanding of the universe championed by a rising generation of physicists. This was a new branch of physics that he had himself inadvertently and grudgingly begun. In his later years, worn down by personal tragedy and horrified at what he saw the Nazi Party do to his country, Planck stood as a staunch advocate for his moral decency and academic truth. This led him, even as a deteriorating octogenarian, to appeal directly to the funny man with the mustache, the man with the funny mustache, to reverse his policy. You know what I'm talking about, right? Jay. Hi.
What?
You know who I'm talking about, right? The man with the funny mustache. To appeal. Oh my god, bro. To reverse his policy of persecuting Jewish academics, He bravely remained in Germany for the duration of the war, working to help those he could flee from tyranny, while he preserved what he could of the country's scientific integrity. Yeah.
Hitler.
So basically, Planck also did other stuff, as in trying to help the country remain scientific integrity-ish. What? Okay. I got through that. Okay, we have 3 sections on this one, and then actually the section after this one has a few equations. So yeah, be ready for that. Anyways, Niels Bohr, quantum theory and the atom. Bohr was born in Denmark to a comfortably off middle-class family. He received a good education and subsequently went to study as an undergraduate at the University of Copenhagen under soil physics lecturer Christian Christensen. That's her name. 1843 to 1917. It was here that Bohr distinguished himself by his personality and potential. His combined traits of tenacity, creativity, and perfectionism saw him working hard and producing impressive work despite significant limitations such as a lack of proper laboratory. It was here that Bohr published his groundbreaking thesis on the problems with modern electron theory. His work was largely unnoticed, probably because it was only available in Danish. Danish? Wait, Blackout, you speak Danish, right?
Why you guess like that?
Danish mother tongue.
But it won Bohr the opportunity to travel to England. Here he began working on the Ernest Rutherford on a new model of the atom. Hold on.
What is Migs's name or nickname on the server? It's like Hergra.
Hergra. Yeah.
Hergra.
Anyways, I already said the Niels Bohr quantum theory and the atom, right? Origin of spectral lines. There's a few equations to this. Actually, I'm going to write down the equations first. Okay. Okay, there's the equation. That's a squared, by the way. For m squared, and n squared. Yeah. Okay, the origin of spectral lines. Light is a part of the electromagnetic spectrum, and it takes the shape of a wave. Like all waves, there is motion up and down, and the distance between each rise and fall is called a wavelength. Visible light fits into a range of about 380 to 740 nanometers, 0.0000038 meters to 0.0000074 nanometers, in which 380 nanometers is a deep violet and 740 nanometers is a dark red. However, most light that we see is actually a mix of different wavelengths, and since Roman times, people have been able to take a glass prism and split the light out into a rainbow. In 1802, William Wollaston, 1766 to 1828, built a specialist telescope and used it to look at the sun. He noticed how the rainbow it produced from the eternal prism was not complete. There were a number of big black lines where part of the color was missing. Over the next 80 years or so, many advances took place in the area of spectroscopy. It was discovered, for example, that burning metals also give off these spectroscopic lines of colors, and each metal emitted different sets of colors. It was also realized that passing electricity through glasses could cause them to glow with the same spectroscopic lights as burning metals. It was soon realized that these lines were probably produced by some kind of effect within the atom. Different atoms in a substance determined whether the colored lines were either removed from the rainbow or emitted from the atoms. This meant that individual atoms were able to absorb or emit certain wavelengths of light. The exact wavelengths they absorbed were unique to each element. These wavelengths give the atom a chemical fingerprint that we still use in identifying chemicals today. In 1855, the mathematician Johann Balmer, 1825 to 98, was working with the pure form of hydrogen gas and looking at the emitted spectral lines. He was able to develop an important formula, this formula right here, where n equals 2, b equals 3.6456 times 10 to the negative 7 meter. Beluga Rhino is playing Marvel Snap.
He always is playing Marvel Snap.
Yeah, and m equals 3, 4, 5, 6, etc. Note, Balmer's original formula uses h instead of b, but has been changed here in order to avoid confusion with the Planck constant, which is given as h. This was later expanded into a more general solution that could be applied to more complex systems. Balmer has successfully shown that these spectral lines came in defined integer values, but the significance of this was only fully grasped when Niels Bohr tackled the problem some 20 years later. Okay. Section done. Do you guys understand any of this? Because I do not.
No.
Totally.
Stop being so enthusiastic, Minx.
Yeah.
I don't understand a single thing.
Exactly. Well, time to actually play Minecraft for a little while. Wait, Jay,
Yes.
look at your screen.
What is my friend sending me?
Loading,
What
share.
is Minx and Michael talking about?
I honestly don't know.
I honestly forgot.
Messages about you. I don't wanna ship Minx and Michael, but I might start doing it now of what I'm seeing.
$10 right now. $10 right now. And I'll do it for you.
Wish I could pay.
For free.
Okay, yeah, I'm gonna put my plate back downstairs real quick. I'll be right back.
You know what? I'm gonna
Do not sussness of anything.
write down the right.
I remember playing Jing Jing Jingle at our Christmas concert. Time to see what they sent me. I am blood. I'm back.
Oh, so we're back.
Yeah. Hold on, let me close my door. Oh, Ghostwalker recently left. Okay.
012 where I live is night.
Okay.
Look at right, it was playing Fallout Shelter.
Yeah. He also played Fallout Shelter today, right? Hey Jay, do you want to play some Minecraft for a little?
What are we gonna do?
I don't know. As of right now, I do not know. There is going to be periodic Minecraft content in the Sonar SMP.
You guys should do a build battle.
Nuh-uh. Oh, what is this?
I would automatically lose.
I'm sick.
I'm sick.
Hey, don't be sick.
Also, chat, how's your day? How's your day, chat? How's your day, chat?
I don't know who's watching the stream.
Me
How many
neither.
people are watching?
2.
Like nobody.
2.
What stream?
I'm streaming right now.
Oh.
They've been
Yeah,
streaming
he's
for
reading the
you
entire.
time,
He's
and
reading.
you didn't know?
I am
He's
not
reading
mentally.
the entirety of quantum theory.
Quantum Theory with a new introduction by James Lee.
I'm so dumb.
Oh, what happened to the amethyst? Didn't it
It's
like
still
die?
here. What you
I can't
mean?
believe Minx didn't know
Or
that.
didn't it like die?
No.
Then what's happening with the amethyst?
It's literally still everywhere.
I know, but why? Why amethyst? Why the amethyst?
Because there's no cure for the thing yet.
You literally sent a cure like in a book and quill in the
Yeah,
studios.
but he has not actually done the cure thing yet.
And what's that blurred thing supposed to be anyways?
What?
I did.
What's that blurred thing supposed to
That's
say anyway?
My favorite word of that.
Hello, Melissa Wires. Yeah,
Melissa Wires was crazy. Oh, you heard survival.
I will murderify all your sheep.
They're not my sheep, they're Alice's.
Oh, okay, never mind. I may have also stolen like one of everything. Like one of every single block that I could farm.
Somebody said hello there, humans in chat.
Yep. Hello
Live
there,
chat.
human human.
Well, some of us
Somebody
aren't
said,
exactly
"Hello there,
human,
humans."
Hey, stop being a furry. Just kidding. I'm just joking.
Why hello there? They
You are
can
one too.
hear me.
You're one too, Corrupty.
I'm actually not.
I just said hi.
You
and I
actually
don't
are,
think they
though.
hear me,
No.
and I hope they can.
I
What?
have my human rights provoked. Wait.
What?
Huh?
I have a cat though.
When you furify your human rights and then furry rights, they're basically same. Why is there an OP iron helmet in here?
What do you mean?
Like there's an iron helmet with like
Wait, Jay.
There's
Jay,
not.
what server is that? I just need to know because if it's
What server is this? What?
you and
This is
Corrupted
a-
are playing on.
This is literally just a world.
Okay, hold on. I need to try something.
What is the
No,
one
no,
we
no,
played
no.
Last time. What world is it?
So
I'm
Do I have
dumb.
you add blackouts on Xbox? The Xbox app?
I don't know. I don't have the Xbox app.
Bro, You're literally on PC. What do you mean?
I am dumb. I'm whispering something and I'm glad nobody can.
Yes, I could do that. Look. Hold on. Look at the iron chest plate real quick.
I'm about to say something so random.
I stole the chest plate.
But Jay,
What?
how is Mr. Matrix's parrot doing? Is it dead or alive?
I don't know. Matrix been offline the entire day.
So I meant his parrot.
I don't know.
What is it? Ooh, free diamonds.
I just want to see that parrot die for some reason.
Thank you, Jay.
What? Huh?
Diamond block.
Thank you.
Blocks are spawning out of me apparently.
Thanks, Jay. You're the best. You're the best, Jay.
There's diamond blocks spawning at me and I don't know why. What the f-
No, Jay is about to turn into diamonds.
No.
Nobody fucking. Oh my god.
Oop.
It broke. Corrupted that right.
Hi.
Thank you.
What happens if
Fleshy.
corrupted spawn?
Thank you.
Spawn bedrock.
Okay.
What happens if corrupted tries to spawn bedrock?
Rush. That's all.
Can I be the hold on. Let me do something. Actually, hold on.
Yeah.
It's slash execute. Okay, I just need to change the values. Or actually, it'll actually. Hold on. Hold on. I'm gonna try something. Let's see if this works.
Don't do anything too chaotic.
Here, I'm just gonna go to the forest real quick. All right. To do it.
You gotta go where?
The forest right here.
Yowie!
Hold on.
I want to say something so random.
I hate
Why?
LVP. Okay, hold on.
Horrible.
Jay's gonna kill me for saying it. Because I used her
What are you gonna say?
like 5 times now.
They do.
I do not know how to run commands.
You gotta use a button on the command block.
I know. Hold on. There. I will be the
Are
disappearment.
you sure you know?
Yes, I'll be the disappearment.
It's repeating now.
Oh,
Oh. That was.
hold on. No, I'm
Oh.
corrupted 1xDA2. Not EMP corrupted. I'm not on that account.
What's corrupted doing with a command block? That's unsafe.
That is gonna make me fall.
Oh. Ah, shoot. Get me out of here. Get me out of here.
Ah,
Get me out of here. Get me out of here. Okay.
Oh, I'm gonna scream Yowie.
Okay.
why
Hold
are you
on.
breaking blocks that are just underneath you when you stand on them?
Because I can. Yeah.
Jingle bells in the background, the most enjoyable song.
We love Jingle Bells. But don't
Who
underestimate it.
doesn't love the jingle ball?
Stop! I'm gonna It's so hard.
I'm sorry, Minx.
That is not about you. It's about all the gifts I got.
What the fuck?
It's-
I thought you said stuff to me saying Jingle Ball.
No. Not all the gifts I got. Oh my god.
Saying Jingle Balls is illegal.
I am reaching this after my gifts up. I don't know.
I can't get a dumb idea out of my head anymore.
No, it's like really hard to control too. It's funny.
Oh my god. I'm so bummed.
Oh no, no, I can't get wood. Quick,
I should probably
Dang it.
I should
Okay.
have been sleeping by now.
the leaves too. Okay, I can finally get wood. But I also have diamonds now.
You don't even need wood anymore.
I do need wood for tools. Spider, get
You almost don't need it
diamondified.
more.
As I'm running around, you'll just see a trail of diamonds. That's just me.
Wait, are you summoning diamonds by walking?
Yeah. Why?
You can't even mine anymore.
I don't have to mine.
Fuck you.
That's a zombie.
What are you doing to the world?
Diamond.
What the
world
hell?
isn't gonna be worlding anymore.
The world isn't worlding. Yeah, probably. Also, hello. I'm just taking a break from reading the book because my mind's going insane.
The stream person I'm seeing in the chat.
Yeah, there's a
I'm
new
just
person.
watching the stream while in the VC.
No,
if people
I got trapped. Oh, okay, good. I didn't get trapped yet. Help me.
I don't know if the person that's in the chat can hear me, but if they can,
No.
I'm just stop turning that world into diamonds, corrupt. Jesus, so many people are gonna join your world and think, what the hell
Oh,
happened to it?
probably. I'm not too sure. Ooh, can I hop walls? Yeah. I can make walls hoppable.
Oh well, hi then.
Okay. Whoa! No, not. I'm not. I don't want to spread. I don't want to spread the. I don't want to spread the amethyst. What are you gonna change the block to next? Or did you destroy the command block?
No, the command block's still on. It should be placing amethyst block. Why was it not? Why
Oh,
is it not placing it anymore?
It's not. In the what's it called? It's not in the simulation distance. So I have to get closer. Yeah. Either you have to get closer, or I'll.
What is corrupted doing to this poor world? Turned it into diamond and now red amethyst.
All right.
Poor
Why is
world.
my anti-aliasing at 16? What the hell?
I
Oh, wait.
don't know.
Can you go near the command block again? See if it works.
The simulation distance is 4 chunks apparently.
I just like how some of the world is diamond.
Here, I'm gonna go mine it real quick. Whose is this? Kill's fishing spot.
The
Not for
world's
long.
just turning into ruby.
It's corrupted amethyst.
What is happening to the amethyst? Jesus Christ, no! This poor world. People are gonna join wondering what the hell happened.
Oh my god.
It's a corrupted amethyst.
It's amethyst.
I mean it fits my name, Corruptor. Corrupted.
I call corrupted corrupto.
I call him Corrupty.
Corrupto here. Corrupto or corruptor?
So if I move this command block closer into the village, it should just work.
Yep, which I'm doing right now.
I wonder.
I already did.
Oh. Execute.
Is it working?
There are 3 streams all happening at once right now. Thanks for the views, though.
There's Christmas music in the background. While Corrupto is turning the world into corrupted amethyst and diamonds.
It's just rare amethyst.
Poor world.
Am I just now the corruptor?
Wait, can it even turn animals into that?
No,
No,
just me.
just blocks.
So I'll corrupt the world, alright?
Oh my lord.
Jay, how are you gonna?
Is this lore accurate, kind of?
Yeah, kind of.
I love
Oh
that.
my god, he's
I'm
only
corrupting the
world.
water.
Yeah, nope. Yeah, Jay, how are you gonna explain this to everyone?
Well, it would make sense for the lore, and that we still need to finish, like the series that I had.
So, the world's being corrupted by corrupted.
Okay, that's actually kind of ironic.
The world is being corrupted by corrupted.
Ooh, I want to play a part as the corruptor. But do you think you could make the amethyst more like deep purple, like, you know, to fit
Lore
the color
says,
theme?
lore says it has to be red.
Oh man, damn the lore.
I just like seeing the lore, but wish I could play a part of it.
Did you get oh, never mind. The amethystification happened again. I'm just trying to learn
I want to see what lore Jay comes up with for this world.
You know, I had a corruption just like this, but it was called the deep slate corruption. Deep slate infection, sorry.
Ah. It's funny, except it's the SMP is amethyst.
It's corrupting the air now. Just have like a random oh, I could border hop now. And I'm corrupting
Oh
the
my
water.
god, he's Jesus Christ.
The world is slowly being corrupted while only Jay is watching and creating.
Slash.
Oh, cause I'm not really recording anything.
Wait. Is it lore accurate that the amethyst can break through bedrock?
It just infects blocks, so probably.
Okay, let's test that theory out. Wait, I can't get under. I can't get under. I can't get under.
So,
Okay.
Yes you can.
Okay, just one block.
That's an escape room from an older video.
Oh. I am the corruptor. I use the powers of corruption. I'm not gonna go to like
Can't wait
everybody
to see
anyone's.
everyone's reactions.
I'm not technically.
This tower's part of the lore.
Oh, can I corrupt it then?
It's already corrupted.
Oh dang. Can I corrupt this guy's house? Like the edges?
No. Well, the edges, yeah, but not the actual house, because Abner spent a while building that.
Yeah. It's pretty decent, but I could see how he could spend like a
what
lot.
happens if Matrix joins?
He's just gonna see me running around corrupting the entire place.
He would just be like,
I am
"Oh,
corrupting the lake. Anyways,
Not even the ice state.
the classical atom. Before we consider Bohr's model, we need to first understand how the atom was being considered at the time. After the discovery of the electron in 1897, J.J. Thomson proposed the plum pudding model. This suggested that an atom was composed of large positively charged ball. Within this ball were contained a number of electrons, as a plum pudding has fruit dotted around inside it. In 1909, however, an experiment was performed by Hans Geiger, 1882 to 1945, and Ernest Marsden, 1889 to 1970, in which they fired charged alpha particles at a thin golden foil. By examining how these particles were scattered or even completely reflected by the foil, Geiger and Marsden were able to determine new properties of the atom. Ernest Rutherford, their supervisor, then used the newly gained experimental results to build a revised model of the atom. Most of the alpha particles that have been launched into the atom had passed right through, suggesting that atoms are mostly empty space. Some were deflected outwards and caused across a spread of angles, suggested that the negatively charged atoms were widely spread out, while just a few particles bounced right back, indicated that there was some large possibly charged central nucleus. The new model of the atom described it as a central nucleus with the electrons moving around the outside, like planets orbiting the sun. Rutherford's model was a step in the right direction, but was still not without significant flaws. In 1911, Bohr was brought into the group to address these. As a theoretician, he was uniquely positioned to try to solve them. The main problem was with the orbiting model was it simply would not work. Radio waves are created using an antenna to make an electron move back and forth. This act of moving an electron causes it to emit energy in the form of electromagnetic radiation. However, this means that electrons orbiting around the nucleus of the center of an atom should be continuously releasing radiation, which would cause them to run out of energy and collapse into the core almost immediately. Atoms are very stable though, and can last significantly longer than the approximately 0.0000001 seconds that the model suggests they could. Something was clearly missing. There's another equation in this chapter, so I am going to switch over to my drawing thing where I put AFK. I hate this. Anyways.
AFK.
Okay, so we have V equals E2 minus E1 over H. Okay, the Bohr model. When Bohr looked at the problem, he saw the experiments were clear. The Rutherford model was at least partially correct, yet the laws of physics did not seem to fit. Bohr turned to some out of the box thinking to solve the conundrum. If the laws of classical physics did not work, what about the new and upcoming quantum theory? To make this new model of the atom, Bohr gave three postulates. An electron can revolve around a nucleus in stationary orbits, which are certain fixed orbits of definite energy without emitting any radiation. Number 2. An electron can make a transition from a higher energy state to a lower one. In doing so, emits a single photon of energy. Conversely, on absorbing a photon of energy, it can move from a lower to a higher energy state. To allow this, the frequency of electron must be as follows, and then this equation right here, where V denotes frequency E1 and E2 are energy states, and H is Planck's constant. 3. Only the orbits where the angular momentum of the electron is an integral multiple of h over 2 pi are allowed. Bohr's first postulate was in fact the greatest insight. The revelation which set his model apart. In it, he sets out the idea of a stationary state where an electron has a particular level of energy and does not emit any radiation. In this state, an electron would be able to orbit around the nucleus indefinitely. His second postulate sets out how electrons are able to move between different energy states. They must do so all in one go, either by emitting or absorbing a photon, particle of light, of a very particular frequency, which must be the same as the difference between the two energy states divided by Planck's constant. Bohr's final postulate set up the rules for ways in which particles are physically able to orbit around the electron. Again, this refers to the all-important Planck's constant, which firmly rooted the new Bohr model into quantum theory. Spectral lines. The postulates that Bohr proposed may have, and at first, seemed rather preposterous, even a little mad. He appears to have arbitrarily decided that it was possible for electrons not to obey the classically understood laws of physics. He had thrown Planck's constant into an equation and made seemingly wild assertions over what kind of radiation electrons could or could not emit. But his claims were not made lightly or chosen at random, and with his new model, Bohr also proposed a solution for the origin of spectral lines. Bohr's second postulate talks about the atoms releasing very specific photons of light. He made the link between this and the spectroscopic lines given off by chemicals. These spectroscopic lines and the equations that govern them are the results of electrons orbiting the nucleus, switching between energy levels. The reason each element gives off different lines is because they have different energy states. Bohr has once stated that spectral lines were seen as the lovely patterns in the wings of butterflies. Their beauty can be admired, but they are not supposed to reveal any fundamental biological laws. Despite such a perception...
Why are we talking about butterflies? What?
Bohr used the spectral lines given off by the hydrogen as the backbone to the proof of the new atomic model. Bohr was able to make his equations fit for the eternity of hydrogen spectrum, explaining previous discoveries that had confused scientists for some time. This was not without a little fudging, however. As the equations did not work for any other type of atom, this became increasingly complex, involving more than just one electron. Despite this, Bohr's explanation was convincing to many. Its flaws were seen as issues to be worked out in the future, but built on top of the solid.
Bohr sounds boring as hell.
Yeah. Thanks. Kuru. My favorite word. What does that even mean?
Kuru.
What does that mean?
Hello there, humans. I'm pretty sure two people watching are the same person. It's the same person, just giving you more views. There are 3 streams all happening at once right now. TBT. Yes, you are. Kuru, my favorite word. Good for you, blackouts.
My favorite word is Flockenhausen amplification. Actually, it's a type between Flockenhausen amplification and pneumonological microscopic silicovolcaniconiosis.
Your favorite word is what?
Hippopotamonstrossus esquis with daleophobia, I think. That's how you pronounce it. I'm not too sure. Or anti-disestablishmentarianism. Yeah. Do you not know how to spell them? Or say them? My bad. Beluga Rhino is playing Fallout Shelter. Beluga Rhino is playing Fallout Shelter.
He would forever be playing that.
Alright, do you think we could change the song to another one?
VCJK. I don't want to force him, but if I had
Yowie!
Okay, let me just get back to the thing. Does it ever go inside your base, Jay?
What?
The amethyst corruption.
It could, but I don't want it to.
Not now.
I feel this person, my brain hurts now trying to understand this.
Okay,
My brain hurts now trying to understand this.
I wonder if they can hear the good Jingle Bell instrumental in the background.
yes, very nice instrumental.
The amethyst corruption shall spread. I'm actually enjoying seeing this spread.
My brain hurts now trying to understand this. Well, if that is so, then we successfully did what we planned.
Ah! I crouched. Okay.
I wonder what happens if Matrix joins.
He's gonna be like, oh god, the corruption's gotten worse.
Just seeing Corrupted doing everything.
I am lore accurate, though.
Even though I don't really have a character yet.
I'm still lore accurate. The tree.
Oh my god.
Accurate.
There's also just gonna be these random structures because you know how amethyst they form like crystals. Haha, zombies! You cannot escape my.
You almost suffocated me.
So is Boar canonical, or is he kind of just like there for no reason, just to tell a story?
He's boring.
Yeah, boring.
I'm
B-O-H-R-I-N-G.
concerned, they say.
Was that pun intentional?
No, Boris is boring. He don't deserve to be a pun.
I think I know you from somewhere, artsy creator, but I don't know. Also, creator's misspelled in your name. It's supposed to be with an O. Just so you know.
Bam.
They have no O in their name.
Exactly.
Well, how do you not know that artsy could be just saying that they're a traitor?
Or
Like
They
an
could be-
artsy creator?
they could be a preposterous turncoat in the war against the amethyst. Okay.
What?
A great success. Bohr's paper was unconventional. It worked to provide an explanation of what was being seen with the spectroscopic lines rather than the pontificate about how the new model might affect other aspects of science, as was the style at the time. Even with this radical approach, Bohr's
I played
idea...
Jigabuzz on the piano.
Oh, nice. Me too. Sorry, I don't remember you from anywhere. It's been so long since I've... Yes, my brain isn't braining as well. Anyways.
My brain does not brain.
Here, chat, if you could spell, actually, don't... You can't turn on captions for this. If you can spell, fucking Austin and Hill Pilification, I will give you 1 subscriber. Doggone.
Why are you freaking acid a hole?
Oh, yeah. My bad. Wait, who is...
How dare you not remember? My brain is not braining. You invited me to the live, dummy.
Oh, yeah, that one. Which one are you?
I did? On YouTube or Discord?
No, probably me. I don't know.
I'm dumb, I'm sorry, I'm dumb, I'm a dumb boy, I'm a dumb with no brain. My brain is not brain.
Brains do not brain.
Okay, where was I? I'll
Brains
just
are
start
not
here.
braining.
Bohr's idea
Well,
was...
we're the brainless group.
My mic just unplugged. Uh-oh. Did the stream crash? Please tell me it didn't. Okay, it didn't. It's just that it just refreshed. The entire setup just refreshed, and it scared me for a second. I thought stream just ended. I'm joining back the VC. Yeah. Okay, I am back. I am back. We are now here. My mic unplugged and I had to restart everything except for the stream. Yeah. Mods, wrap him up and gift him to the Grinch. Metalheads when I bury magnets outside the house.
May they help you on the way.
Captain, why did you leave the VC?
Because my mic crashed. Yes, you heard that out.
Oh.
Yeah, you heard that right. My mic crashed. Anyways.
I don't remember.
The 1913 meeting of the British Association for the Advancement of Science took place just a few months after. The The 1913 meeting of the British Association for the Advancement of Science took place just a few months after his first publication on the topic. J.J. Thomson, the leading scientist and creator of the
J.J.
rival...
Thompson.
The leading scientist and creator of the rival plum pudding model began the meeting by describing Bohr's work as an igneous and suggestive, and I think that we
I'm gonna go get some more.
must
cola.
add convincing explanation of
Insignia.
spectral series. Thomson added that the only justification at present put forward for these assumptions is the very weighty one of success. Even Albert Einstein was amazed by Bohr's work, declaring it to be an enormous achievement.
You taped off my kind.
Oh. Despite such scientific endorsement, not everybody was convinced. Many of his contemporaries were still skeptical about quantum theory, and such a leap was for them a step too far. Some even decided that Bohr's work was the result of either a fraud or a madman. Eventually, however, Bohr's postulate became largely uncontested. Some scientists became convinced by further discoveries and experimentation. Others, especially those who were incoming, younger and less cooperative in approach, were more open to quantum theory and accepted Bohr's ideas. Over subsequent years, Bohr received numerous accolades for his work. He became a member of important institutions and was invited to give talks all over the world. Even after his death, his face was printed on stamps and money. Bohr was also the recipient of a huge number of awards, such as the Hughes Medal, the Franklin Medal, and the Copley Medal. In 1922, he even received the Nobel Prize for Physics in recognition of his services in the investigation of the structure of atoms and of the radiation emanating from them.
My legs are not legging.
The Frank-Hertz experiment of 1914
I heard
an
somebody joined the
accelerated
VC.
electron beam fired.
Who is it? Is it my Pookie Michael?
Can I read? Can I read? No, it was chicken. It's chicken. The one that's usually pain in the. Okay. Solidifying science. The Frank-Hertz experiment in 1914 used an accelerated electron beam fired into a gaseous form of mercury. I keep reading the E because I'm practicing Russian, so I keep thinking yeah. The current measured across the chamber would increase as the energy of the electrons was increased before reaching a point whereby it would suddenly drop off, then increased again, before falling several times. This was because at certain energies the atoms were able to absorb the electrons, causing the current to drop. The experiment also showed that mercury too had these discrete energy levels without resorting to the same spectroscopic science previously used. This further confirmed the existence of atomic energy levels. While Bohr's model was a success in itself, it was the science that was able to follow it that truly made his work spectacularly important. With a proper explanation of its mechanics, spectroscopy could grow quickly as an area of study. A host of standard techniques were developed and used to examine chemicals for industry and research, as well as in exploring the chemical composition of distant stars. The acceptance of the idea quantized energy states in atoms also allowed for a wealth of advances across many scientific fields, not least nuclear physics and chemistry, both of which gained fundamental insights from the new model. Continuations in quantum theory. Bohr was the first to admit that his model was far from perfect. He acknowledged that it had never been designed to be a complete picture, and spent many years working on his ideas and helping the study of quantum theory grow. In 1921, he established the Institute for Theoretical Physics at the University of Copenhagen, later named after him, for which almost immediately became a hub for physicists studying and developing quantum theory. By the mid-1920s, Bohr's atomic model was quickly becoming surpassed, yet it had remained the forefront of quantum theory. Attending conferences, corresponding with other important scientists, and encouraging new theories from his increasingly eminent position, not least of his roles as an advisor to Werner Heisenberg, who would go on to develop the uncertainty principle, another foundation piece of quantum theory that Bohr would champion. The quantum mechanical atom. In 1958, after discussion with another scientist, Wolfgang Pauli, 1900 to 58, about the latter's discovery of the Pauli exclusion principle. In quantum theory, Bohr declared the problem with his own atomic model to be that despite the leap forward it has been facilitated, it was not crazy enough. Bohr and other top scientists, he theorized, had been too cautious about fully committing to quantum theory. They had instead adhered to classical ideas with just a little quantum mixed in. This was to change in 1926 when another scientist, Erwin Schrödinger, 1887 to 1961, dragged the model of the atom fully into the quantum realm. Schrödinger used his new quantum mechanical equation known as the Schrödinger equation to describe the electrons found around the nucleus as existing in possibility space. That is to say that the electrons are described not as individual particles on orbits around the atom, but rather as a cloud of possibilities where the electron might be and how likely it is to be there. This was a full embrace of founding tenet of quantum theory uncovered by Max Planck years earlier. The idea that quantum mechanics is inherently statistical, Bohr had noted immediately on seeing the discovery of his assistant Heisenberg uncertainty principle, it would cause the spreading out of the frequencies. This in turn would imply some sort of statistical effect. Schrödinger's model of the atom was much stranger and more difficult to understand than Bohr's had been. Its introduction of properties such as suborbitals and probability clouds led to further understanding in aspects across physics and chemistry. For example, the van der Waals effect. This statistical model remains the foundation for our understanding of the atom even today. The Second World War. Following the rise of the Nazi Party in Germany during the 1930s, many Jewish academics began to flee the country. Bohr worked to give them temporary jobs and accommodation within the Institute for Theoretical Physics of the University of Copenhagen, where he found them roles at other institutions around the world, further away from Nazi influence. He even went as far as to dissolve the Nobel Prizes of several fleeing Jewish academics to hide the valuable objects from the Germans. In April 1940, German troops invaded and occupied Denmark. Bohr's efforts to shield Jewish academics had to become more clandestine, and in September 1943, he found out that due to his mother's heritage... You scared me. Beluga Rhino is playing Fallout Shelter. April 1940, he was... In September 1943, he found that due to his mother's heritage, he was considered Jewish. He pressed the king to declare openly the country's willingness to take in Jewish refugees. This declaration was made and led to around 7,000 Danish Jews managing to escape to Sweden. From Sweden, Bohr moved on to Britain and eventually in December 1943 to the U.S., where here he had involvement with the Manhattan Project, never becoming a member of the team, but lending his now considerable experience and insight into atomic physics. He also used his fame to meet with important people, impressing upon them the dangers of the atomic bomb and working to ensure that any such development would be done safely and with proper oversight. Modern perceptions. In physics, even a landmark paper, one that sets up a new branch of physics and alters the very way we think about the world, is quickly subsumed into general understanding. So it is not surprising that 120 years later, you will not find references to Planck's work. Despite its groundbreaking nature for science, even the slightly more recent work of Bohr, similar in its importance and impact, is unlikely to feature in a modern scientific journal. Walking the halls of any modern physics department, you would struggle to find anyone who actually read the papers, or even a library that had a copy on the shelf. However, this is not to say that the ideas in Planck and Bohr had been consigned to theory. While the works themselves may now hold real value only as historical objects, signifiers of the landmark discovery made, the ideas that they contain relevant today as then. Science is an inherently collaborative process. Discoveries are built on top of discoveries. And the great Sir Isaac Newton 1643 to 1727, observed in a letter to his scientific rival Robert Hooke. 1635 to 1703, if I have seen further, it is by standing on the shoulders of giants. So while the actual works themselves may not be so important to modern physics, where an entire field of study can be turned on its head every few years, their influence is still very much felt. Beyond the direct work that the two men achieved, their advocacy and support of physics was crucial for much of the immediately following in work in quantum theory. The Niels Bohr Institute and Max Planck Institute remain two of the foremost places of learning, even if their focus has expanded just beyond just quantum theory. All of this has meant that the names of Bohr and Planck remain some of the most respected in the field and show no sign of fading anytime soon. Also, footnote 1, Bohr tasked in the chemist in his laboratory, George D. Hevesi, 1885 to 1966, literally to dissolve the metals of James Franck, 1882 to 1964, and Max von Laue, 1879 to 1960 in Aqua Regia. The bottle was then placed on a shelf in the lab. After the war, they returned to find the bottle still in its place. The gold was precipitated out of the acid and eventually recast into new copies of the metals. Okay, Planck's enduring legacy. Planck's equation E equals hv remains one of the fundamental postulates that underpin quantum physics. The quantization of energy is a principle that stands at the heart of quantum mechanics and has led to the development of many ideas, including photons and the subsequent photons and plasmons. Sounds like a Pokemon ripoff, which all treat particles and waves such as much as the same thing. The postulate that quantum theory is non-deterministic and statistical in nature also played a large role in how physics developed. It shaped not only the equations that followed, but also much of the rationale behind the ways in which future ideas were and continue to be explored. Planck's constant h, or its alternative h with the funky line through it, equal to h divided by 2 pi, are some of the most commonly used constants in physics. They appear in almost every quantum equation you could come across, showing the direct influence of Planck's work. Bohr's model utility. Bohr's model of the atom has fared less well there. By the 1920s, his atomic theories were in trouble, and as a concept that worked well enough for hydrogen, struggled and broke down when applied to other elements, especially those composed of more electrons. It is important to note that this was not necessarily unexpected. Bohr had never presented this idea as a complete solution. Moreover, while Bohr's model of the atom has been quickly improved upon, it remains one of the clearest and most popular ways to describe the workings of an atom. The Bohr model provides...
Interrupted, we're trying to get a crowd. There's 8 people in the voice chat now.
The Bohr model provides a useful example of the scientific concept of building on past work. The fact is deemed incorrect by most accounts does not mean that it has ceased to be useful. The popular conception of an atom, the picture that an average person would draw if asked, is not far off one of Bohr's own original sketches. In relatively simple cases, in effect anything before university level science, the Bohr model tends to be good enough. It could give a broad understanding that explains some of the larger properties and may even be used to develop technologies if the minutiae is not too complex. To draw an analogy, you do not need to expertise in chemistry to bake a cake, even though the processes and effects are chemical. A paradigm shift. Fortnite reference?
What?
Paradigm. Oh. Why is my wolf here? I guess you're here now.
What about the wolf?
It's mine. Okay. Okay. Anyways. Okay. Paradigm shift. The true importance of the work begun by Planck and then carried on by Bohr is something that goes beyond either of the individual scientists. Quantum theory caused a seismic shift in way people thought about the universe, an enormously important achievement and something that much of this introduction has focused on. Scientifically speaking, it was the beginning of a new epoch. The discovery of quantum theory is an event equivalent to many ways the work of Archimedes, 287 to 212 BC, in applying mathematics to physical problems, in the introduction of scientific method by Galileo, 1564 to 1642, or Newton's
I've heard of that man.
Or Newton's discovery of universal laws in calculus. I hate calculus so much. It was the uncovering of a new bedrock
Edition.
on which to build scientific discoveries, causing scientists to re-examine all the work that come before. Another angle not examined in detail here is the philosophical implications of a quantum world. The founding tenets of quantum theory declare our universe to be statistical, which led to a dismayed Einstein famously writing in a letter to Bohr,
I, at any rate, am convinced that he, God, does not throw dice.
The potentially terrifying philosophical conclusions of quantum theory are often pointed to as some of the reasons for the initially slow uptake of the idea. They remain something with which scientists and philosophers continue to struggle today. It is here that we should note caveat with quantum theory. I do not know how to pronounce that. It may not be true, as with the classical understanding of the universe that preceded it. There's a possibility of some deeper understanding that we have yet to find. Scientists continue to work on examining the world through a quantum lens, but in the back of their minds lies the thought that another groundbreaking discovery could be just around the corner. Physics continues to work towards understanding the world around us, and any sensible scientist would refrain from saying that there is little left to learn. Okay. Do you like the book so far? Is everybody...
Well, why are you reading this again?
Why not? Okay.
You know, Krypton, if you wanted to, you could probably build like a little reading pedestal, like little stage thingy, like in the main village.
Sure. Okay.
I would you might want to get rid of the command blocks that are making it to where you're spreading the amethyst.
Okay.
I can hop borders now.
What are you, Mexican?
Yeah. Yes. Wait, no, I'm stuck.
Okay, it's still spreading, so there's a freaking command block somewhere. Oh my god, you're spreading it everywhere.
Actually,
Is it done now? Are you still spreading it? Yep.
I don't know how to get rid of it.
You gotta break the command block that you made that's make it to where you spread it.
I went far enough away.
Oh my god. There's a command block somewhere. There should be a command that just allows you to destroy all the command blocks.
Wait, how many command blocks do you even have in this world?
The ones that you placed were the only ones.
Wait,
I did not
What?
get.
Huh?
I want to restart.
There's still more command blocks?
yep, got rid of it now. I am.
Are you
a
still
genius. I didn't look at chat. I promise. I promise I didn't look at chat.
Why are you still spraying the amethyst? Jump scare, yeah, and that scared me even more because I'm a VC. I could join VC if I wanted to.
I actually didn't look at chat. I promise you. I promise you I didn't. But yeah.
In fact, I could join the VC if I wanted to. They stare into the viewer's soul. Well, that stare scares me. Same. A little scoof from them was everything. Jay looking into that dog's soul for real scary. Jay looking into a dog's soul. Then he stares into the viewer's soul. Yeah, mountain somewhere lies.
Okay, where should I build the thing?
What is chat talking about? I said like in this like area where there's like nothing right now. This where I'm hovering.
Rookie.
Okay.
Who are you calling Pookie in the chat?
Huh? Who?
Get back
Or
to
my-
the rice fields.
Oh.
Stop texting me back!
Lies, I did join VC. It's trippy. Yeah. How is the VC trippy? What?
Oh, maybe because the audio. If you're watching the stream and the VC at the same time.
I have the stream muted, so.
Ah, I see.
Wait, were you in the VC? People here are also in the VC listing.
I'm so sick.
Mm.
I feel so sick.
Is Artsy the raccoon woman guy person thing?
I do not know.
Oh, I felt so sick.
Don't say that ever again. Raccoon?
My brain. Why is everyone's brains not braining? Come on, it's just simple theory.
Where the heck do you find the chairs? This isn't spawn eggs?
Yo guys, where's that Christmas music? Whoa.
I just...
Who is it? Who is it?
It's Jesse.
Yeah, that's just
Okay.
me.
Make sure to be like quiet. I'm reading something. And also do not say anything racist like you usually do.
so stressed.
Who's getting attacked?
Chair.
Oh.
He's playing an anime game. Cool. Michael
Well, we're
now
not
is
playing
here.
an anime game. We're just playing the
Okay.
funny block game.
Alright, I'm gonna start reading again. I'm gonna start reading again. Alright.
Left. That's weird.
Okay, the modern study of quantum theory. Quantum mechanics, the modern name for quantum theory, is now one of the most important fields of study within physics. It is a core part of any university course and informs much of the fundamental academic research that occurs, even beyond aspects actually focused on quantum theory. Outgoing research has thrown up more and more bizarre consequences of the quantum nature of our universe. These range from the fact that heat is inherently a quantum effect to the discovery of vacuum particles, which can appear out of nowhere and interact with the world around them before popping out of existence again. The quantum phenomena we now know about, built upon the work of Planck and Bohr, fill the volumes of...
Blankenbohr, what the fuck?
Planck and Bohr.
Plank. Oh.
Planck. Yeah, Planck. P-L-A-N-K-C-K. Where was I?
Blank.
Planck and Bohr fill volumes and volumes. A couple of these are explored briefly below. You may
What kind of name is Plank?
wooden planks. You may have heard of Schrodinger's cat, an experiment in which a cat is placed in a sealed box with a vial of poison that has a 50-50 chance of breaking and killing the cat.
What?
The idea
Why are we killing cats?
the idea then is that before the box is actually reopened, the cat exists in a superposition of states. It is both alive and dead. Only when you open the box to observe the results does the cat stop spamming me, Noah Brown.
What guy? Last name is Brown.
Okay. Sorry, someone is spamming me.
Well, then tell him not to spam you.
I am. Become one or the other.
Say, don't spam me. I'm trying to read quantum theory.
While this is an intentionally strange example, the effects are very real. The instance of another quantum phenomenon has been demonstrated through experiments carried out using individual photons of light. The photon with the ability to pass through either of two slits will impossibly seem to pass through both at the same time, thus creating an interference pattern. But when special equipment was set up to observe exactly what was happening, the photon only passed through one, no longer creating the interference pattern. Quantum tunneling is an effect that pops up whenever you look small enough. Imagine a ball bouncing inside a box. Classically, we would say that so long as the walls are strong enough.
Eyes are not eyeing, yeah, no one. Them casually killing a chair.
Oh.
Someone was killing gas? Oh god, my joke didn't work. This is funny, VC, not gonna lie.
Okay.
Yeah.
Classically, we would say that so long as the walls are strong enough that the ball can bounce back and forth as much as you like, as long as the box remains sealed, it cannot escape. In the quantum world, however, we often do not consider particles as a singular object. As in the quantum theory of the atom that replaced Bohr's model, the particles can be treated as areas of probability. In our box scenario of the right scale, there is some small probability that the particle is outside the box. Therefore, because there is a tiny statistical chance that could be the case, a particle is sometimes able to escape its normal confines based on sheer probability. Applications of quantum. The uses of quantum mechanics in devices are broad and myriad. Many modern electronic devices such as MRI machines, flash drives, lasers, and numerous types of scientific instrumentation already employ quantum effects to make them work. The expected technologies to be born from the quantum theories in future years are also exciting. Quantum mechanics also become increasingly important as our technologies become smaller and smaller. Modern electronics are reaching incredible scales. The latest microprocessors now fit over 30 billion transistors per square millimeter, in each of which measures less than 10 nanometers, the width of less than 100 atoms. This size is expected to keep falling, and below 7 nanometers, a scale just about possible today, quantum effects begin to kick in. Once 5 nanometers was thought to be the end of Moore's law, the physical limit...
The fuck is a nanometer?
Nanometer, really small meter, just like you.
Oh.
The physical limit at which transistors could be made to function. Beyond this scale, the quantum effects of tunneling, where electrons are able to pass through a barrier by sheer statistical chance, start to reach a level at which a transistor would no longer be reliable. However, after scientific study in Korea in 2006, a 3 nanometer transistor was produced. By early 2019, several companies announced commercial products expected to be released in 2022 using just such a size. Such developments in modern technology would not be possible without our increasing understanding of quantum theory. This knowledge will only become more important as things inevitably scale down even further, possibly reaching
Remember, kids, size does not matter.
Well, it depends on what.
Possibly reaching components that are subatomic in size and rely wholly on quantum effects in the strange world of
Tell me at the age
For
difference.
real, Magic Adams, do you want to know what the best donut that was ever made? Sure. What's this best donut that's ever made? Blackout.
In the strange world of quantum technology, it is
A Ran Goku
Don't
donut?
kick me out.
I'm actually gonna time you out if you... Okay.
What?
Anyways,
What?
in this strange world of quantum technology, it is very difficult to predict what will come next, as the secrets of quantum mechanics continue to be uncovered. Once one of the most exciting areas of quantum technologies is in quantum computers. These use qubits, which are superpositions of states, such as the direction of spin of a single electron, as opposed to classical computer bits. Successfully creating a quantum computer could lead to an exponential boom in computing power. This in turn could lead, in just a decade or two, to a difference greater than that between today's computers and those first built in the Second World War. Unfortunately, for now at least, the elusive quantum computer is a long way off. However, as governments and businesses continue to pour resources into solving the problem, a visionary such as Bohr or Planck might be all that is required to solve a seemingly unrelated issue and get the ball rolling. New Horizons, the future of our quantum world. It is hardly possible to speculate where the future of quantum theory lies. The effects of Planck's discovery are still being felt today, over a century later. Countless lives dedicated to the study of the quantum world, along with huge sums of money, have still only resulted in scientists scratching at the surface. The questions that we now face from quantum physics grow more numerous by the day. Every discovery seems only to show that there is much more to find. Many scientists are focused on the uses of quantum technologies. They explore how the theories and quirks of quantum universe can be harnessed to improve people's lives, whether through computers, electronics, or even medical processes. Others continue to examine the fundamental ideas of quantum theory. Here they use the latest experimental techniques, technologies, and ideas to probe the most basic part of our universe, always seeking to learn more about how it ticks. Whatever may happen, quantum physics seems to be here to stay for the foreseeable future. A difficult pill to swallow.
Arctic.
Quantum mechanics is crazy. Although its application we can find that matter can pass through walls, nothing is really where we think it is, and our universe has upon it fundamental limits for the allowed energies for a seemingly arbitrary reason. If you ever feel at a loss, do not worry, you're not alone. The prominent U.S. theoretical physicist John Wheeler, 1911 to 2008, was reassuring. Nothing. If you are not completely confused by quantum mechanics, you do not understand it. Even the great Richard Feynman,
What is bro yapping
1988, one of the most influential of post-war theoretical physicists, observed, I think I can safely say that nobody understands quantum mechanics. The complexities and difficulties mean that most people leave quantum theory well enough alone. Even many career physicists take great pains to avoid having to delve too deep into it. This becomes increasingly difficult to do, however, as quantum theory takes a larger and larger role in modern science. Erwin Schrödinger, creator of the Schrödinger equation, one of the most fundamental and widely used pieces of quantum mechanics, expressed in his own unease at quantum theory, I do not like it, and I am sorry I ever had anything to do with it.
Why do you keep changing your accent every once in a while when you're reading the book?
It's a quote. As a species, we can often feel comforted by our scientific knowledge. There is so much we know about the world around us, offering apparently rational explanations and predictability, and so much that we could do to control it. When it comes to studying quantum theory, however, we may feel, although we are stumbling around in the dark, lacking even the smallest inkling of what is going on. As such, given the rate of our scientific discoveries, it is impossible to say what our understanding of quantum theory will look like in 10, 20, or even 10 years' time. Two great works, the papers and subsequent work of Max Planck and Niels Bohr, stand as important milestones in the history of physics and science as a whole. Both may have been adopted slowly, with their importance understood over time and eventually embraced. Much of the scientific work that has occurred over the following decades has been affected, directly and indirectly, by the ideas of quantum theory. To this day, Planck and Bohr are rightly celebrated. Even if they do no longer stand at the forefront of academic research, the founding role they played has made its mark and continues to be felt in the quantum theory. Whatever the future may hold, the work of Planck and Bohr will continue to be important for as long as science, as we currently understand it, exists.
I like how this is the one thing you thought of doing for a Christmas thing.
Yeah. Both men have already found their place in history alongside Newton, Einstein, and of course, some of the first scientists of ancient Greece. Their work still forms the basis of even the most modern, cutting-edge science and continues to be taught to a high level across the world. Even should new discoveries surpass quantum theory in its entirety, the insights of Planck and Bohr should remain important as an adequate way to explore less complex systems, much as Newton's work has, and as a major part of the scientific community journey. James Lees. Okay, that was just the intro So now we're going into chapter 1.
That was only the intro?
Yeah. Okay. Page 36, and there's 479 pages, just so you know. I'm not gonna read the entire thing today. I'm probably gonna read up till... Actually, let me set a goal. Oh, there's a lot of equations, just so you know. A lot of equations.
Oh, yay.
So you'll see me drawing a lot more. My drawings are horrible. Okay, I'm gonna stop at page 111 today.
That's a lot of pages.
Not too many.
Imagine if Matrix just randomly joined while you're freaking reading quantum theory.
Huh?
Imagine if Matrix just randomly joins the VC when you're reading freaking quantum theory.
Yeah. He's gonna... His mind's gonna blow.
He's literally gonna explode.
Yeah, you should invite more people, actually. Just kidding. You don't have to, but it'll be much appreciated. Also, subscribe if you haven't already. And this is gonna be... I'm going to keep reading this. I'm gonna restart it from the beginning until I get 5... No, I'm gonna read my entire library until I get like 1,000 to 2,000 subscribers. Okay. Actually, I'll take a break for now. I'll also be doing other streams other than Minecraft. Oh, thanks for adding more decoration.
Both the people in the voice in the freaking stream chat are saying we're gonna die here.
Yeah.
Yes, you will, and we will consume your souls after it.
Everybody that
I thought you
dies
said we would sue their souls.
sue their... Oh yes, sue their souls.
Like, what are we gonna go to court? Ace attorney?
Yes, indeed. That's exactly what's gonna happen. Totally.
Yeah.
This stage, I want to add like seats to it, but the stage things take up like most of the front of the front thing.
I lost my feet.
Manort plan Bornil Nicalian.
There you go.
I'm gonna be continuing the next part in what's it? Few days.
The castle?
No, I'm gonna continue the next part in a few minutes. Let me just take a breath with my mouth. I mean, I'm so done.
This is lore stuff.
Won't stop me.
It's lore stuff that's already known, so...
Okay.
Yeah, there was loot here. Oh, there was loot here. School.
There's gonna be a chair there for loot.
There's a castle that a bunch of people in the realm helped build
Wow,
for an
my
episode.
Soul ate me. My soul ate me. Can you change it to another Christmas song, please? So, someone in VC, please. No! Okay, I accidentally entered the phone. FICO.
I already lost my soul, Jay. I don't have one, so good luck. Satan took my soul. I hate mine. Songs that
soul
stuck
ate
my
me.
mind.
Okay, best excuses for homework. My dog ate my homework. No. My
Pretty
homework-
little,
My homework ate my
pretty
dog.
little psycho. Little same.
Okay, my dog ate my homework, my homework ate my dog. I ate my homework ate me. I ate my dog ate me.
No.
Wait, I already went this way. Did I do an entire thing still? It's not here.
Who is asking to change the song?
Me.
Why?
It's been repeating for so long, like add variation.
It's the 10-hour version.
Nah!
I sentenced you to 10 hours of Jingle Bells.
At least there's a clarinet part. Can't go wrong with clarinets, can you?
Let's play a new song.
Squidward.
Let's play the ball song.
Why is Soul Say not working?
I'm failing.
2 hours? Only 2 hours? I could go for so much longer.
I don't want to miss.
Okay, Blackouts is now asking to change the song. You know, any of you guys, including me, could just change the song right now. We just choose not to because we're lazy.
So, me and a bunch of my other friends built the base of this and, like, the actual
And then somebody
exterior.
else finished it, yeah, I know.
And then somebody, remastered it with this tower.
It's pretty mediocre, no offense.
Damn.
It's not working.
And how many hours did this take?
Quite a few.
This looks actually really simple to build.
It takes forever to build, though.
Yeah, just because of the actually, let me see. Yeah, I guess because of the walls, and also so there's supposed to be another one here because it's just one. I'm not gonna question it. And then yeah, that.
Like, you could build a better castle. You probably could.
Most likely, yeah. And there's parkour, which I failed already.
Yeah, this was one of the members
forgot
that are
the
no
commands.
longer in the Snar Things idea. We banned somebody from the Snar group.
Oh, they
So-
griefed, right? Didn't someone grief it?
Well, that, but a different it was a different person that we removed because we still don't know who griefed it.
Well, I mean, I wasn't even in the Star SMP at that time.
Oh, exactly. So it's not you. I never said it was.
This song is the music is making me insane.
No, it'll copyright me. It'll copyright me.
Oh no,
Frick you. Frick you, Blackout. Frick you.
it wasn't even me.
Frick you,
What the hell?
Blackout. Frick you. Who changed it then?
What did I do?
All I want for Christmas. It was Mario.
Mario.
It was freaking Christmas Mario.
Oh my god. I'm gonna have to ban him for that.
Why is everybody muted except for us three?
Because the guy with the crab just kicked me out for no reason because I was talking. Like that's why I muted myself.
The guy with the what?
Sleeping mother.
It's like a crab, the average furry.
Wait, when was
I'm
this
purely
going?
muted because I am concerned.
Anyway, no,
No.
not important.
I'm muted because I am in a room with my sleeping mother.
Whoa.
Why?
You
Whoa.
I'll beat your ass. Oh.
What? I'm already back here. What? Oh. Oh, what is this?
All I want for Christmas is you.
Okay.
What the hell?
I'm gonna be continuing the reading now. In this dark dungeon, I read silently.
Deck the halls of Christmas jolly. La
Okay.
la la. I
If-
forgot the
Okay,
lyrics.
if I flip heads, I read. If I flip tails, I will stop reading. I mean, I will not read.
Oh, someone join.
Is Deck the halls copyrighted?
Dude, I freaking stop.
Well, I'm
Oh,
trying to play
Michael.
music for the stream. What?
Yeah, try to find non-copyright. I don't know if it's copyright. Just Try to find not.
I don't think any like the OG Christmas music is copyrighted because Jingle Bells isn't.
Hold on, let me search.
I
But I swear, if I get copyright strike, I know who I'm looking for.
It's not a strike. It wouldn't be a strike. It would just be a claim.
I know. That's what I mean. My brain's not braining. I've been reading too much quantum theory. The quantums are quantizing.
Then your brain should be braining by 10 times.
No, it's unexpected. It's quantumizing. Ah! Hold on.
Is Christmas music copyrighted?
Is Christmas music copyrighted? Certain music is copyrighted. What is that? Your worst nightmare.
In general, most classic and traditional holiday songs are public domain. That means if you want to cover one of the Christmas classics, chances are you won't need any license. So, pretty much any Christmas music, any Christmas song is just not copyrighted.
Okay, who just kicked me out of the VC? Yeah, I'm gonna find
Who kicked him?
Audit log.
Okay, it was Mario.
It's Mario. I'm gonna revoke him. For
I think that guy just left.
He's going.
Mario, stop being a bully.
I don't know, buddy.
Oh wait, no, not like
Mario. Bad Mario.
They're not even in the VC.
They were even annoying this morning.
I don't know why he's kicking. I don't get why he's kicking
anyways.
everybody.
If I flip heads, I will read. If not, it'll be 1 minute.
He's poking.
Okay, it's heads, so I have to Okay, I'll have to read now. I hate this. Yes, you're my only viewer. A new introduction for this edition to Albert Einstein, Erwin Schrödinger, and Werner Heisenberg.
Please don't. How to change it? I'm your only viewer now. Yes.
Okay. 10,000 great works. Max Planck and Niels Bohr were, of course, only the start. Quantum theory had its central idea and building blocks, but it has required the work of many thousands of scientists working over lifetimes to get us to where we are today. Each paper that they have published is...
Why are you in the zombie room, corrupted?
True quantum enlightenment. Such papers could be considered, like all scientific texts, as great works in their own right. Reading all these is simply not practical, so included here are a few of key texts written by those who were on cutting edge of their field and are still recognized for their brilliance today. The drown's looking at us, just staring into your soul, Jay. Albert Einstein, on a heuristic point of view concerning the production of transformation of light. We have briefly covered Albert Einstein's solution to Planck's ultraviolet dilemma. Its importance cannot be overstated, however, which is why his original paper have been included here. Einstein is perhaps the most famous scientist of all time, and although some of his other contributions to physics may be better known, his work on quantum theory was no less significant. Apparently not content with revolutionizing 3 different fields of physics in a singular year, 1905, through his explanation of Brownian motion, the discovery of special relativity, and his famous equation E=mc², Einstein also provided the first real experimental evidence of Planck's quantum of action in his attempt to explain the photoelectric effect. The problem may be summed up as it follows. It is possible to get a material to release electrons if a light is thrown upon it. This is because the atoms within that material are surrounded by electrons. However, atoms do not give up their electrons easily.
Do notifications appear on your stream?
I
Like
don't think so.
if someone texts you in Discord? No?
Anyways, Where was I? Okay. However, atoms do not give up their electrons easily either. Energy is required to release the electron from its normal position orbiting the atom. Rather, as a rocket needs energy to escape the pull of Earth. The amount of energy needed to do is called the work function, and it varies from one material to another. Light is a form of energy. Consequently, it is a very... There's going to be a lot of equations, so I'm just going to switch over to animation desk real quick. Yeah. Okay. As I was. Light is a form of energy. Consequently, if a very strong light source is shown at something with a low work function, such as certain metals, that material can be made to emit electrons. These electrons can then be measured in an electric circuit.
Oh god, he's like a broken record.
When the light is turned on, an electric current begins to flow, which is caused by electrons being released from the material. The problem was that this did not always happen due to something called an intensity problem. Scientists realized that if the light was above a certain wavelength, i.e. the distance between the peaks and troughs of the wave, the current would never flow at all. A longer wavelength of beam of light may have less energy, but if the light is delivered as one continuous wave, a concept widely believed at the time due to a series of previously performed experiments over a long enough period of time, it should be able to deliver the same amount of energy and get the electricity flowing. However, this did not happen. It did not matter how long the light was shining or how bright it was. If the wavelength was too long, it simply would not work. Quantum enlightenment. Einstein's genius found the explanation to lie in the quantized photon. The energy in each individual photon is solely determined by its wavelength. In order to free the electrons to flow around the circuit, all of the required energy has to be absorbed from a single proton. Increasing the intensity only increased how many photons were hitting the surface, not while the length of time was no longer played any role. The theory fit the facts. It simply had to be a quantum effect. No other explanation was possible. Not only did this insight bring about some of the first real experimental proof of quantum theory, but it also predated and in some ways preempted the understanding of light being both a wave and a particle. Ooh, jazz saxophone. Einstein's explanation certainly showed that light was made of discrete particles, but also revealed that they also had distinctly non-particle properties, such as wavelength. His work stands as a simple but profound paper that was specifically name-checked when he won the Nobel Prize in Physics in 1921, awarded to Einstein for his services to theoretical physics and especially for his discovery of the law of the photoelectric effect. I'm going to drink some water real quick.
Officially been 3 hours since we started.
I have winter break now, so I could do this series like within the winter break. Okay, yeah. Okay, there's gonna be an equation coming up, so I'm gonna have to delete all this.
I just sent you an encyclopedia.
Huh? Wait, DJ, when were you here?
In here.
Yeah, when were you here?
I really need to pack my food. Basically, it was like a couple minutes after I said I could join VC. I just need help with them.
Equations. Wait, chat, do you want, if we get enough people in chat, maybe like 5 unique people, or I mean, different people, I can give you guys equations that you have to solve, and then I'll give you like, I don't know. I will give you cookies. So, if you can invite everybody you know.
The other person is watching.
Huh? Yeah, there's only one other person. but still.
There's two people watching, me and then one other person.
Okay. Erwin Schrödinger, I think that's how you pronounce it, collected papers on wave mechanics. Schrödinger is famous for his rather absurd analogy of a cat that is both dead and alive, but his contributions to quantum theory are far more important than his pop culture status might suggest. Within the collected papers, Schrödinger sets out the formulatic foundation of the entire field. The mathematical basis from which all quantum effects arise can be calculated. In no other place is this better shown than his magnificent time-dependent Schrödinger equation, which is this. Hold on.
Great.
He's drawing equations. Oh, fuck, why are you drawing a trident?
I don't know what it is. Okay, anyways. This particular formulation is a cleaner and more modern version than the one used in the original papers included here. However, Schrödinger nonetheless uses his equations to solve the quantum mechanical state for a single hydrogen atom. He proceeds to use his implications to examine much more of the world through this new quantum formula. There is no simple explanation for what the formula is or what it does. In essence, it describes the wave function of a quantum mechanical equation. It describes the wave function of a quantum mechanical system. It is an equation that outputs all of the possible answers for the thing being measured and for their likelihood. This is where the cat comes in. Because the equation describes all the possible states, a creature can both be dead and alive at the same time. A scientific equation such as this, able to describe everything that could possibly happen, might sound like something out of a science fiction, rather like Isaac Asimov's Foundation, first published in a series of short stories between 1942 to 44. Sadly, however, it is unlikely to be useful in predicting the future, as Schrödinger sets out in his papers. The calculations and various factors that need to be considered within the calculations are difficult and get complicated very quickly. Even the creator of the equation himself does not.
Did you know you've been live for 3 hours?
I know. Does not go much further here than describing the Schrödinger equation for that single hydrogen atom, the simplest thing in the universe. More than some of its parts. As important as its namesake formula is, that is not all.
Is it? I can't tell.
I'm turning this bot down.
Please do not change the music for the bot. We're trying.
No, I'm not even gonna do anything with the bot. I'm turning it down on my side.
Okay. Scientific equations such as this. Okay, never mind. Sadly, however, it is unlikely to be useful in predicting the future, as Schrödinger sets out in his papers the calculations and variations.
So Matrix.
Let me finish this paragraph real quick. The calculations and various factors that need to be considered within the calculations.
It's okay.
And get complicated very quickly. Even the creator of the equation himself does not go much further here than describing the Schrödinger equation for that single hydrogen atom, the simplest thing in the universe. Yeah, I just had to reread that. Anyways, you could tell.
What, Jay?
Corrupted is streaming and he's reading the entirety of what is it?
Quantum theory.
Quantum theory. He's been doing this for 3 hours straight.
Didn't he send me a video about that?
Maybe.
Bro, I got a video saying like that. I'm like, wait, what? I just said nice. Didn't say anything else.
Quantum theory reading, part 1.
Okay. More than the sum of its parts. As important as his namesake formula is, that is not all that Schrödinger covers within his
Kidding me?
Part of his genius was his ability to pull in the theories and equations developed by a host of other scientists across a range of subjects, at which first glance might seem quite disparate. Combining such ideas as Hamiltonian mechanics, a companion method to Newtonian mechanics, and the electromagnetic ideas of Lawrence Maxwell can be difficult. But it was always a passion of Schrödinger's, to such an extent that for many years he sought to produce a grand theory of everything. GD reference! Theory of everything.
Oh, no!
Able to combine all the there's a GD reference. Theory of everything. Able to combine all the physics under a single set of usable equations. It was a grand ambition, but one that drew desertion, even
Jay, what are you
derision,
doing?
even from Einstein.
Watching corrupted stream.
Despite
He's not even
Schrödinger's
streaming for me. He's not even streaming for me.
He's on YouTube streaming.
Oh.
You
okay. This set of papers
don't
also,
lobotomize yourself.
despite Schrödinger's best efforts, it remains
Little
unsolved
house.
to this day. This set of papers also offers an incredible insight
I
as
stream.
each
I stream.
was written sequentially, with the earlier papers being published
Yeah,
before calculations were made for the latter ones. This affords us the opportunity to join a great scientist in his work as he goes through the process of discovering something new. Additionally, Schrödinger was in some ways much as a philosopher as he was a scientist. Even here, in one of his most analytical works, you will find that the spark of his interest in the broader meaning and implications of his text shines through, adding some levity to what can be a very dense set of mathematical formulas. Okay, I'm taking a break there. Quick. So then that you guys can talk
I
a little bit.
stream.
You scream.
Hey, Stream, say
All
hi to
scream
him.
for ice cream.
Yeah, Rosie the cat.
Also,
SCP,
make-
like 600 something, I think.
Yar.
Rosie
What are
the
you
cat. Are you
playing?
talking about the SCP,
I'm playing
Or,
Roblox.
I mean, not Jay. Whatever your
Stream
name is.
playing Roblox. I mean, I haven't heard of a game called Roblox, but I know a game called Roblox.
Yeah, that SCP, the half cat,
Oh my
cat.
god.
But it's not really it's not really.
Why is there so many
depicting
drowns in here?
It's not depicting Rosie in any way.
I know it
mean,
wasn't.
it's-
I just happened to think of it when I heard
Yeah,
it.
yeah, because he's
Leave me
half
alone.
dead, he's kind of dead and kind of alive.
After what? And it didn't mention a cat, so.
I should have recorded a podcast episode of this, but not really.
It sounds
Okay.
so weird.
Podcast episode 1: Decoding the entirety of quantum theory.
There's no.
Honestly, that sounds like a bad idea.
This is just chaos.
Yes. Welcome to the Chaos Stream where your brain gets absolutely deatomized.
Don't worry, guys. Jay is gonna die because he's frozen.
Rules to him, and then
How
just
is
realize
that got anything to do with what we were talking about, Matrix?
Because I will unfreeze you by the end of this month.
If Jay's gonna take the
Bro,
photo.
enough of the unfreezing.
I've dropped my phone on my face like 6 times because I'm holding a computer in one hand, my phone in the other.
I'm
How are
holding
you,
a-
why are
Yo,
you
Mario
holding a
just blocked
computer in one hand?
Mario just blocked me.
Because I can't find my computer
crazy.
spinning, it's overheating, so I have to hold it in the air.
I'm holding a fish.
Fish!
I have a key. Please, computer sucks.
All right.
Why am I so fucking slow?
The Heisenberg
Because the
principle.
phone's laggy.
The Heisenberg principle. However, Heisenberg's elegance in tying together the work of his peers and the
Is the
overall
story
field
time?
should not be allowed to overshadow his own significant contribution to quantum theory. Not only was he a key figure in the creation of matrix mechanics, not one of the mathematical equations.
The
Matrix, you're in
mechanics?
quantum theory.
Matrix mechanics. Not
Matrix
yeah.
mechanics.
One of the mathematical
Matrix
equations.
theory, quantum theory.
Yeah. He's canonical to quantum theory. That rivals the Schrödinger equation. But he
Hey,
also
Jay, I made a cameo.
okay.
No way.
Not only was he a key figure in the creation of the matrix mechanics, one of the mathematical methods for understanding quantum theory that rivals the Schrödinger equation, but he also developed another key equation that bears his name, the Heisenberg uncertainty principle. Slope. I think this is slope of x, I'm not too sure. Times slope of
No,
x
that's great. That's so great.
is greater than or equal to h over 4 pi.
Can stream hear us, by the way? Because I'm not even
Yeah.
watching the stream.
Yeah.
Yes.
Once again, the above equation is a more modern interpretation. This you will notice it differs slightly from the equation that Heisenberg spends the first part of physical principles deriving. This equation states that the uncertainty of the position of a particle x multiplied the uncertainty of a particle's momentum p must always be equal to or larger than the value of h divided by 4 pi. As we established earlier, the Planck constant h has a very small value, so normally we do not need to worry about this. When we get down to the scale of quantum, however, it becomes very important. Okay.
Don't you do
Oh, did
that?
Blackouts and Matrix left?
Yes, they did.
This equation states that the uncertainty of the positions of a particle x multiplied by the... Okay, I already read that. This sets up a new unsolvable mystery. On the very small scale of atoms and subatomic particles, quantum theory states that we can never fully know exactly where a particle is or what speed it is traveling at, as momentum is based on speed. Now, not only has quantum theory broken the idea of deterministic universe down to one based on statistics, but it also says that to show the true answer is itself against
What
the
the
laws of
hell
physics.
is bro yapping about?
Exactly. Hurrah. Hurrah. What are you yapping about?
I'm playing a horror game. But technically, please.
I'm so okay trying to read this my brain.
Okay.
I swear to God, if Broski grabs me, I'll be.
Okay. This is not just the case for position and momentum. A similar uncertainty equation was later developed for energy and time, which allows the unimaginable to happen. Logic tells us that something cannot be created from nothing, but with uncertainty it can. Before, we mentioned particles popping in and out of existence, and it is through uncertainty that it happens, so long that they have a low enough energy and are only around for a tiny fraction of a moment, because they are allowed to exist. It might seem absurd to say that just because an equation allows it, such a thing might actually happen. Vacuum particles, i.e. particles that appear from the vacuum of nothing, have been seen to exist, however showing us once again just how bizarre our quantum world is. On reading a scientific paper. A scientific paper does not make for light reading at the best of times. They are designed to transfer knowledge in a succinct way between academics and students. This can lead to them being filled with seemingly impenetrable equations and needlessly specific wording. This is particularly true in the works collected here, which are much older. The language used can also seem somewhat strange to our modern eyes. However, the entire reason why such works exist is to spread their knowledge. They are created to teach things to others. As such, while reading them may at first be difficult, they are designed to be understood. This will likely take time, patience, and a considerable amount of rereading, along with a not insignificant amount of time considering some formula or another. But the reward of a deeper understanding is greatly worth it. In quantum theory, more than in most other fields of science, it is vitally important to have a proper understanding of the finer details and the underlying equations. This is simply because the results can hardly be believed, and it is only through the rigorous application of great scientific minds that we can appreciate them. It is this for a reason. It is for this reason, for the scientific theory that changed forever how we understand the universe in which we live that these works are so vitally important. James Lees. Okay. The intro is now done. I think chapter 1.
Intro.
That was kind of starting of the
Ow.
intro, but
Wait.
that was like, hold on. The great works. Hold on, let me check contents real quick. Okay, we're on part 2 now, actually.
They shall die.
Okay, I'm gonna stop on part 3, alright, guys? I'm getting kind of tired of reading this. I'm gonna chat real quick. Michael Balls. Jason R, yes. RC created 2 more, then we could do trivia. Okay. Actually, do you want to do trivia now?
Oh no.
Do you want to do trivia now?
Trivia?
Anything but having to sit here and listen to this any longer.
Okay, I'm gonna give you an easy one.
My brain's off. Can't take it any longer.
I'm so stupid.
What blood?
Matrix has arrived. Again.
Hey guys, graph this equation right here.
Someone has moved.
Open up Desmos and graph this right here and send me a screenshot of what it looks like. And then you'll see the point of game.
Go fuck.
Re. I will win this battle. Re.
What is going on?
I will win this battle.
The hell?
I win.
Nuh-uh. Re.
Hornet.
Wait, is Corrupted still streaming?
Yeah, I'm still streaming. I'm taking a break real quick.
Okay.
Yeah.
Good.
You're supposed to be doing trivia.
I feel like Mario's autistic for some reason.
Who, Mario?
Yeah. He got mad at me for nothing, over nothing.
What? Hi, Pookie.
What do you mean? It's not Pookie, it's Poopy. What are you talking about, bro? It's Poopy. What are you talking about, bro?
Poopy.
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 Look.
Like Poobay?
I started another Corrupted Thinking Space server, you know that, right?
You started a what?
Another Corrupted Thinking Space server, you know that one?
Can I please join that?
Yeah, hold on.
Wait, did you just delete the other one?
Yeah. So then that nobody from the OG people can find it.
Why does Michael always come after me? What the bro?
What do you mean? What
Bro,
did
I
Michael
said
do?
poopy as a joke. He said, shut the fuck up.
Because he doesn't.
Okay. Okay. I'm gonna
Hey,
continue
yo.
reading.
Hey, no.
Okay, I only have 20 pages, or less than 20 pages actually. So, okay, let's go.
20 damn
Great
pages.
works that shape our world. Max Planck, The Origin and Development of the Quantum Theory, translated by H.D. Clark and L. Silverstein. The Origin and Development of Quantum Theory. My task this day is to present an address dealing with the subjects of my publications. I feel I can best discharge this duty, the significance of which is deeply impressed upon me by my debt of gratitude to the generous founder of this institute, by attempting to sketch in outline the history of the origin of quantum theory, and to give a brief account of the development of this theory and influence on the physics of the present day. When I recall the days of 20 years ago, when the conception of physical quantum of action was first beginning to disentangle itself from the surrounding mass of available experimental facts, and when I look back upon the long and tortuous road which finally led to its disclosure, its development strikes me at times as a new illustration of Goethe's saying, "A man errs so long as he is striving," and all the mental effort of an assiduous investigator must indeed appear vain and hopeless if he does not occasionally run across striking facts which form incontrovertible proof of the truth he seeks, and show him that after all he has moved at least one step nearer to his objective. The pursuit of a goal, the brightness of which is undimmed by initial failure, is an indispensable condition, through by no means a guarantee of final success. In my own case, such a goal has been for many years the solution of the question of the distribution of energy in the normal spectrum of radiation heat. The discovery by Gustav Kirchhoff that the quality of the heat radiation produced by an enclosure surrounded by any emitting or absorbing bodies whatsoever, all at the same temperature, is entirely independent of the nature of such bodies, established by the existence of a universal function which depends only upon the temperature and wavelength, and is entirely independent of the particular properties of the substance. And the discovery of this remarkable function promised as deeper insight to the relation between energy and temperature, which is the principal problem of thermodynamics, and therefore also of the entire field of molecular physics. The only road to this function was to search among all the different bodies occurring in nature, to select one of which the emissive and absorptive powers are known, and to calculate the energy distribution and the heat radiation in the equilibrium with the body. This distribution should then, according to Kirchhoff's law, be independent of the nature of the body. The most suitable body for his purpose seemed H. Hertz's rectilinear oscillator dipole, whose laws of emission for a given frequency he had just then fully developed. If a number of such oscillators be disturbed in an enclosure surrounded by reflecting walls, there would take place an analogy of sources and resonators in the case of sound, an exchange of energy by means of the emission and reception of electromagnetic waves, and finally what is known as blackbody radiation, corresponding to Kirchhoff's law, should establish itself in the vacuum enclosure. I expected, in a way which certainly seems at the present day would somewhat naive, that the laws of classical electrodynamics should suffice, if one adhered sufficiently to generalities and avoided two special hypotheses. hypotheses to account in the main for the expected phenomena and thus led to the desired goal. I thus first developed in as general terms as possible of the emission and absorption of a linear resonator. As a matter of fact, by a rather circuitous route, which might have been avoided when I used the electron theory, which had just been put forward by H.A. Lawrence. But as I had not yet complete confidence in that theory, I preferred to consider...
Minx, you tell us to stop arguing, but he keeps freaking going, so I can't do nothing.
I preferred to consider the energy radiation from and into a spherical surface of a suitably large radius drawn around the resonator. In this connection, we need to consider only processes in an absolute vacuum, the knowledge of which, however, is all that is required to draw the necessary conclusions concerning the energy changes of the resonator. The outcome of this long series of investigations, of which some be tested and were verified by comparison with existing observations, e.g. the measurements of Bjerknes on damping, was the establishment of a general relation between the energy of a resonator and of a different free frequency and the energy radiation of a corresponding spectral region in the surrounding field in the equilibrium with it. The remarkable result was obtained that this relation is independent of the nature of the resonator and in particular of its coefficient of damping, a result of which was particularly welcome since it introduced the simplification that the energy of the radiation could be replaced by the energy of the resonator, so that a simple system of 1 degree freedom could be substituted for a complicated system with having many degrees of freedom. But this result constituted only a preparatory advance towards the attack on the main problem, which now towered up in all its imposing height. The first attempt to master it failed, for my original hope was that the radiation emitted by the resonator would differ in some characteristic way from the absorbed radiation, and thus afford the possibility of applying a differential equation, by the integration of which a particular education for the composition of a stationary radiation could be reached, was not realized. The resonator reacted only to those rays which were emitted by itself, and exhibited no trace of resonance to neighboring spectral regions. Moreover, my suggestion that the resonator might be able to exert a one-sided, i.e. irreversible action on the energy of the surrounding radiation field called forth the emphatic protest of Ludwig van Boltzmann, who with his more mature experience in these questions succeeded in showing that according to the laws of classical dynamics, every one of the processes I was considering could take place exactly in the opposite sense. Thus, the spherical wave emitted from a resonator when reserved strengths in concentric spherical surfaces of continuously decreasing size onto the resonator is absorbed by it, and so permits the resonator to send out again into space the energy formerly absorbed in the direction from which it came. And although I was able to exclude such singular processes as inwardly directed spherical waves by the introduction of a special restriction, to wit the hypotheses of natural radiation, yet in the course of these investigations it became more and more evident that the chain of argument and an essential link was missing, which should lead to the comprehension of the nature of the entire question. How many pages of that one? Holy crap. That's a long one.
God just stops the entire conversation.
There's like 10 pages of this. Okay. The only way out of the difficulty was to attack the problem from the opposite side, from the standpoint of thermodynamics, a domain in which I felt more at home. As a matter of fact, my previous studies on the second law of thermodynamics served me here in good stead, and that my first impulse was to bring out not the temperature but the entropy of the resonator into relation with its energy, more accurately not the entropy itself but its second derivative with respect to the energy, for it is the differential coefficient that has a direct physical significance for the irreversibility of the exchange of energy between the resonator and the radiation. But as I was at that time too much devoted to pure phenomenology, phenomenology to inquire more closely into the relation between entropy and probability. I felt compelled to limit myself to the available experimental results. Now, at the time in 1899, interest was centered on the law by the distribution of energy, which was not long before where was it? Which had not long before been proposed by W. Wien. The experimental verification of which had been undertaken by F. Paschen in Hanover and by O. Lumer and E. Pringsheim of the Reichsanstalt, Charlottenburg. This law expresses the identity of radiation in terms of the temperature by means of an exponential function. On calculating the relation following from this law between the entropy and energy of a resonator, the remarkable result is obtained that the reciprocal value of the above differential coefficient, which I shall here denote by R, is proportional to the energy. This extremely simple relation can be regarded as an adequate expression of Wien's law for the distribution of energy, for the dependence on the energy that of the wavelength is always directly given by the well-establishment displacement of
Jay, do you see what I'm
V.
freaking talking about?
What?
Freaking being freaking rude.
What?
Michael.
Yeah, kind of.
He's being rude to me and Jay. That's what he's doing.
I could talk to him.
Apparently, Bro does not understand what neutral face is.
First of all, Mink, I said that as a joke. He doesn't have to find it funny.
I know. I know.
Oh my god.
I know.
So when can I continue the story and actually get this
You
stream
can
done with?
continue the story, but we're gonna continue our crap here in the chat, okay?
Okay, yeah. Just talk about it in the chat. Since this whole problem deals with the... Hold on, actually, let me put on some more Christmas music.
It's easy to get
I
lost
hate
in investment
ads.
research. Introducing JP Morgan Personal Advisors.
Hey, David.
Connect with an advisor to create your personalized
Let's
plan.
find the right investments for your goals.
Okay, great.
JP Morgan Wealth Management.
Bro thought the neutral face was a furry thing. Crazy.
Don't spend another dime on Amazon until
Bro.
you watch this first. Watch this.
Whoever added that boy, I wanna punch him in the face so bad, bro.
Okay.
Oh, I
Since
didn't even
this-
realize that the music stopped.
Since the whole problem deals with the universal law of nature, and since I was then, as today, pervaded with a view that the more general and natural law is the simpler it is, although the equation as to which formulation is to be regarded as a simpler cannot always be definitely and unambiguously decided. I believe for the time that the basis of law of distribution of energy could be expressed with the theorem that the value of R is proportional to the energy, but in view of the results of new measurements, this conception soon proved untenable. For a while, Wien's law was completely satisfactory for small values of energy, and for short waves. On the one hand, it was shown by O. Lumer and E. Pringsheim that considerable deviations were obtained with longer waves, and on the other hand, the measurements carried out by H. Rubens and F. Krillbaum with the infrared residual waves, Reststrahlen of fluorspar and rock salt, disclosed in a totally different but under certain circumstances very simple relation characterized by the proportionality of the value of R not to the energy but to the square of the energy. The longer the waves and the greater the energy, the more accurately did this relation hold. Thus, two simple limits were established by direct observation for the function. R, for the small energies, proportionality to the energy; for large energies, proportionality to the square of the energy. Nothing, therefore, seems simpler than to put in general case R equal to the sum of a term proportional to the first power and another proportional to the square of the energy, so that the first term is relevant for small energies and the second for large energies, and thus was found in a new radiation formula, which up to the present
Jay,
has
why? Why?
experimental examination
Well, you know what,
fairly
the
satisfactorily.
Eggo waffles.
Nevertheless, it cannot be regarded as having been experimentally confirmed with final accuracy, and a renewed test that be most desirable. But you, oh wait, you can do, what happened, Jay?
Eggo waffle.
Did you send that in chat, the Eggo waffle?
He sent me that picture twice already, because you sent it to him, bro.
Okay.
That's some cake.
Bruh.
Okay, continuing. There is no equations for the foreseeable future, so I'm going to move this over here. Okay, but even if this radiation formula should prove to be absolutely accurate, it would, after all, only be an interpolation formula found by happy guesswork, and would thus leave one rather unsatisfied. I was therefore, from the day of its organization, occupied with the task of giving it a real physical meaning, and this question led me along Boltzmann's line of thought to the consideration of the relation between entropy and probability, until after some weeks of the most intense work of my life, clearness began to dawn upon me, and an unsuspected view really revealed itself in the distance. Let me here make a small digression. Entropy, according to Boltzmann, is a measure of a physical probability, and the meaning of the second law of thermodynamics is that the more probable a state is, the more frequently it will occur in nature. Now what one measures are only the difference of entropy and never entropy itself, and consequently one cannot speak in a definite way of the absolute entropy of a state. But nevertheless, the introduction of an appropriately defined absolute magnitude of entropy is to be recommended, for the reason that by its help certain general laws can be formulated with great simplicity. As far as I could see, the case is here with the same energy. Energy too cannot itself be measured, only its differences can. In fact, the concept used by our predecessors was not energy but work, and even Ernst Mach, who devoted much attention to the law of conservation of energy, but at the same time strictly avoided all speculations exceeding the limits of observation, always abstained from speaking of energy itself. Similarly, in the early days of thermochemistry, one was content to deal with heats of reaction, that is to say, again with differences of energy, until Wilhelm Ostwald emphasized that many complicated calculations could be materially shortened if energies instead of calorimetric numbers were used. The additive constant, which thus remains undetermined for energy, was later finally fixed by the relativistic law of the proportionality between energy and inertia. As in the case of energy, it is now possible to define an absolute value of entropy and thus of physical probability by fixing the additive constant, so that together with the energy, or better still the temperature, the entropy could still vanish. Such considerations led to a comparatively simple method of calculating the physical probability of a given distribution of energy in a system of resonators, which yielded precisely the same expression for entropy as that corresponding to the radiation law, and it gave me a particular satisfaction, in compensation for the many disappointments I had encountered, to learn from Ludwig Boltzmann of his interest and in entire acquiescence in my new line of reasoning. Yes, Matrix?
Number one, I didn't know that you were on a logo of a Eggo waffle brand.
I wasn't.
Oh
no.
God. Because as you can see, Jay sent me a picture of somebody on an Eggo waffle brand, and yes, I know you sent him that, but I think that's you on the Eggo waffle box.
Is it a red
He's
wolf?
a gray.
No,
He's
it's a red wolf.
He's gray.
It's you on the Eggo waffle box.
That's bagels.
It's not a red. It's not a red wolf, so it's not corrupted.
It's orange. What are you talking about?
It's literally beige.
Bro.
It's more orange.
Guys.
It's like a light orange.
Y'all are so colorblind. It's green.
Nah, it's purple, bro.
It's literally blue.
Thick and fluffy, femboy furry made with extra woo in no G. Belgian style.
Belgian style.
I'm not Belgian.
I want to eat it. I want to see how it tastes.
Are glow sticks dangerous to eat?
But since Jay said it was me on the logo, don't eat me.
No, I didn't say. I did not say it was.
I'm in Matrix. My bad.
Hey.
Okay. Anyways,
It's not a red wolf, so it can't be. It literally can't, because it's not red.
To work out these probability considerations, the knowledge of two universal constants is required, each of which has an independent meaning, so that the evaluation of these constants from the radiation law could serve as a posteriori test whether the whole process is merely a mathematical artifice or has a true physical meaning.
What are you talking about?
The first constant of a somewhat formal nature, it is connected with the definition of temperature. If temperature were defined as the mean kinetic energy of a molecule in a perfect gas, which is a minute energy needed, indeed, this constant would have the value of 2, but in the conventional scale of the temperature, the constant assumes instead of 3 an extremely small value, which naturally is intimately connected with the energy of a singular molecule, so that its accurate determination would lead to the calculation of the mass of a molecule and of associated magnitudes. This constant is frequently termed Boltzmann's constant, although to be best known of my knowledge, Boltzmann himself never introduced it, an odd circumstance which no doubt can be explained by the fact that he, as appears from certain of his statements, never believed it would be possible to determine this constant accurately. Nothing can better illustrate the rapid progress of his experimental physics within the last 20 years than the fact that during this period not only one, but a host of methods have been discovered by means of which a mass of single molecule can be measured with almost the same accuracy as that of a planet. While at the time when I carried out this calculation on the basis of the radiation law, an exact test of the value thus obtained was quite impossible, and one could scarcely hope to do more than test the admissibility of its order of magnitude. It was not long before E. Rutherford and H. Geiger succeeded by means of direct count of this symbol on screen right here. I think, yeah, this symbol right here of that particles in determining the value of electrical elementary charge as 4.65 10 minus 10 10 the agreement of which with my value 4.69 nice 10 minus 10 could be regarded as a decisive confirmation of my theory. Since then, further methods have been developed by E. Regener, R.A. Millikan, and others, which have led to but a slightly higher value. Much less simple than that of the first was the interpretation of the second universal constant of the radiation law, which, as a product of energy and time amounting on the first calculation to 6.55 10 minus 25 ERG second, I called the elementary quantum of action. While this constant was absolutely indispensable to attainment of the correct
I didn't know you had a job, Minx.
For entropy for only
Yeah,
if it's A.
my OnlyFans.
What?
You just said that on the stream, bro.
Fuck you, Minx. Fuck you, Minx.
Hey, bro, you just said that on the stream. Yeah, you got caught, bro. You got caught red-handed.
Could be determined the magnitude of the
I didn't mean to
elementary
get
region
caught.
or a range of probability necessary for the statistical treatment of the problem. It is obstinately withstood all attempts at fitting it in any suitable form into the frame of classical theory, so long as it could be regarded as infinitely small, just like UJ and Matrix.
What?
That is to say, for large values of energy or long periods of time, all went well.
No.
But in general, case of a difficulty arose at some point or other, which became more pronounced as the weaker and more rapid than the oscillators. The failure of all attempts to bridge this gap soon placed one before the dilemma. Either the quantum of action was only a fictitious magnitude, and therefore the entire deduction from the radiation law was illusory, and a mere juggling with formulae, or there is a bottom of this method of deriving the radiation law some true physical concept. If the latter were the case, the quantum would have to play a fundamental role in physics, heralding the event of a new state of things, destined, perhaps, to perform completely our
He's
physical
destined for greatness.
Our physical concepts,
Shut up.
which, since the
Respectfully.
introduction of the infinitesimal calculus by Leibniz and Newton, have been founded upon the assumption of the continuity of all causal chains of events. Experience has decided for this. Beluga Rhino is playing Worm Online.
Crazy.
Magic.
Respectfully, Jay, shut up.
Experience
No.
has decided.
Yes.
Respectively, both of you, can you please shut up? Experience have decided for the second alternative, but that the decision could come so soon and so unhesitatingly was due not to the examination of the law of distribution of the energy of heat radiation, still less to my special deduction of my law, but to the steady progress of the work and of those investigators who have applied the concept of quantum of actions to the searches. The first advance in this field was made by Albert Einstein, who on the one hand pointed out that the introduction of the quanta of energy associated with the quantum of action seemed capable of explaining readily a series of remarkable properties of light action discovered experimentally, such as Stokes' rule, the emission of electrons and the ionization of gases, and on the other hand, by the identification of the expression for the energy of a system of resonators with the energy of a solid body, derived with the formula for the specific heat of solid bodies.
He's rapping.
Which on the whole represents
Desecration, decimation. If you want to bring it to the masses,
respectively, shut up. It correctly as a function of temperature, more especially exhibiting its decrease. Especially you, Minx. You've been the loudest ever.
Especially Minx.
Yeah. A number of questions were thrown
What
out.
did I do?
Shut up, Minx. In different directions, of which the accurate and many-sided investigations yielded in the course of time much valuable material. It is not my task today to give an approximately complete report of the successful work achieved in this field. Suffice it to give the most important and characteristic phase of the progress of the new doctrine. As to thermal and chemical processes with regard to specific heat of solid body. Einstein's view, which rests on the assumption of a single free period of the atoms, was extended by M. Born and Th. von Karman to the case which corresponds better to reality, viz. That of several free periods, while P. Debye, by a bold simplification of the assumptions as to the nature of free periods, succeeded in developing a comparatively simple formula for the specific heat of solid bodies.
Did you just say to the Matrix?
No.
Oh.
Represents its values,
Well, how did I get so many pictures on Rec Room? What the hell? Why is everybody taking pictures of me on Rec Room?
Especially
why?
Especially those for low temperatures obtained by W. and Ernst and his pupils, at which moreover Minx, shut up, is compatible with the elastic and optical properties of such bodies, but the influence of the quanta asserts itself also in the case of specific heat of gases, and the very
Why is there so many
Minx,
pictures of my amateur
shut
Rec
up!
Room?
Minx, shut up! At the very outset, it was pointed out by W. Nernst that did I already no that to the energy quantum of vibration is that I'm looking at that word wrong. Vibration must correspond. No, that's correct. Vibration must correspond an energy quantum of rotation, and it was therefore to be expected that spacing error. There's a spacing error. The rotational energy of gas molecules would also vanish at low temperatures. This conclusion was confirmed by measurements due to A. Yuckin of the specific heat of hydrogen, and of if the calculations of A. Einstein and O. Stern and P. Ehrenfest and others have not yet decided completely satisfactory agreement. There is no doubt is due to our imperfect knowledge of the structure of the hydrogen atom. That quantized rotation of gas molecules, i.e. satisfying the quantum condition, do actually occur in the nature can no longer be doubted, thanks to the work on absorption bands in the infrared of N. Burum, E. V. Barr, H. Rubens, and G. Hettner, and others. Although a completely exhaustive explanation of the remarkable rotation spectra is still outstanding. Since all affinity properties of a substance is ultimately determined by its entropy, the quantum calculation of entropy also gives access to all problems of chemical affinity. The absolute value of the entropy of a gas is characterized by Nernst's chemical constant, which was calculated by Sacker by a straightforward combinatorial process similar to that applied to the case of oscillators, while H. Tetrode, holding more closely to experimental data determined by consideration of the process of vaporization, the difference of entropy between a substance and its vapor. While the cases thus far considered have dealt with states of thermodynamic equilibrium, for the measurements could yield only statistical advantages for large numbers of particles and for comparatively long periods of time. The observation of the collisions of electrons lead directly to the dynamic details of processes in question. Minx, shut up. Therefore, the determination carried out by J. Frank and G. Hertz of the so-called resonance potential of the critical velocity of which an electron impinging upon a neutral atom must have in order to cause it to emit a quantum of light provides a most direct method for the measurement of the quantum of action. Similar methods leading to perfectly consistent results can also be developed for the excitation of characteristic X-ray radiation discovered by C.G. Barkla, as can be judged from the experiments of D. L. Webster, E. Wagner, and others. Okay, Minx, what do you want to say, because you can't seem to shut up?
I have a question now.
Yeah.
How many more pages?
Huh?
And how many more pages?
8. So,
okay.
So do you want me to get done with it now and then we can talk later? Do you want me to get done with it now and then we can talk later? Or do you want to, like, take breaks in the middle?
Well, Jay, are you playing Ransom right now or are you looking at the video?
But you know what goes really good with
I am looking at the website.
Jay, do you want to play the Rec Room or no?
I mean, we could.
I'm on it right now.
I was just looking at rec.net and apparently a bunch of people take pictures of me for some reason.
Bro!
You're a fan. I mean, you're a...
You're a what? You're a fan?
Yes, I blow air at people.
Guys, the frozen snar is offline.
Yeah, you want to know what goes really good with quantum physics? Apparently?
Well,
Trying to fix it.
Okay,
yeah, so
do you want me to continue now?
Yeah,
should we, yeah, just get it over with at this point so we can talk later.
Let's go. The inverse of the process of producing light quanta. I'm basically speedrunning this by the impact of electrons.
He's rapping.
Stop! Freaking. Just
interrupting.
Shut up, Minx. X-rays. And here too, the energy quanta falling from the action. Quantum and Haha. Period play a characteristic role.
I wonder who's gonna get blamed next.
As was early recognized from The striking fact that the velocity... Bro, shut up, Minx. Of the emitted electrons depends not upon
They're not
the
even
intensity,
here!
but only on the color of the impinging light, but quantitatively also the relations to light quantum, pointed out by Einstein, have proved successful in every direction, as was shown especially by R.A. Millikan by measurements of the velocities of emissions of electrons. While the importance of the light quantum is inducing photochemical reactions was disclosed by E. Warburg, although the results I have hit her to... What?
Minx is talking again.
Shut up, Minx.
They're not even here.
I know, I just wanted to see what
from
he's
the
saying.
most diverse chapters of physics, taken from in their totality, form an overwhelming proof of existence. The quantum of action, the quantum hypothesis received is also its strongest support from theory of the structure of atoms. Quanther? It's Quanther.
Quanther?
Shut up, Minx.
What if I just...
Quantum theory of spectra, proposed and developed by Niels Bohr. For it was the lot of this theory to find the long-sought key to the gates of the wonderland of spectroscopy, of which the discovery of the spectrum analysis up to our days had stubbornly refused to yield. And the way once clear, a stream of new knowledge poured in a sudden flood, not only over this entire field, but into the adjacent territories of physics and chemistry. Its first brilliant success was a derivation of Balmer's formula for the spectrum series of hydrogen and helium, together with the reduction of the universal constant of Rydberg to known magnitudes, and even the small differences of Rydberg constant for these two gases appeared as a necessary consequence of the slight wobbling of the massive atomic nucleus, accompanying the motion of the electrons around it. As a sequel came the investigation of other series in the visual and especially the X-ray spectrum, aided by Ritz's resourceful combination principle, which only now was recognized in its fundamental significance. But whoever may still have felt inclined, even in the face of this almost overwhelming agreement, all the more convincing in the view of an extreme accuracy with spectroscopic measurements, to believe it to be a coincidence must have been compelled to give up on his last doubt when A. Summerfield deduced by a logical extension of the laws of the distribution of quanta in systems with several degrees of freedom, and by consideration of variability of inert mass produced by the principle of relativity, that magic beluga rhinos playing Terraria.
Crazy.
Oh, it's going great. It's going great, Jake.
Can we do like an NPC thing where I'm like just like using the quick chat things?
Look at me, Jay. Look at me, Jay. Wait, hold on. Let me get to where I can. Wait, can I use the chat? Oh yeah, I can use the chat.
Where was I?
I had nothing. I can look back like 2 seconds in the thing. real
That
quick.
magic formula before which the spectra of both hydrogen and helium revealed the mystery of their fine structure, as far as this could be disclosed by the most delicate measurements possible up to the present, those of F. Passion. Those of S. Passion, a success equal to the famous discovery of the planet Neptune, the presence and orbit of which were calculated by Leverrier and Adams before man ever set eyes upon it. Progressing along the same road, P. Epstein achieved a complete explanation of the Stark effect of the electrical splitting of spectral lines. P. Debbie
Jay, what do you want to play?
obtained a simple... Stop
I
talking,
don't
Mings.
know.
Stop talking, Mings. A long series. X-ray spectrum investigated by Mann, Siegbahn, and then followed a long series of further researches which illuminated with greater or less success than the dark secret of atomic structure. After all these results, for the complete exposition of which many famous names would here have to be mentioned, there must remain for an observer who does not choose to pass over the facts no other conclusion than the quantum of action, which in every one of many and most diverse processes has always been the same value, namely 6.5210 10 minus 27 ERG second thank deserves to be definitely incorporated into the system of the universal physical constants. It must certainly appear a strange coincidence that at the same time as the idea of general relativity arose and scored its first great success, nature revealed precisely in a place where it was the least to be expected an absolute and strictly unalterable unit by means of which the amount of action contained in the space-time element can be expressed by perfectly definite matter, and thus is deprived of its former relative character. Of course, the mere introduction of the quantum in action does not yet mean there was a true quantum theory has been established. Nay, the path which research has yet to cover to reach that goal is perhaps not less long than that from discovery of the velocity of light by Olaf Romer to the foundation of Maxwell's theory of light. The difficulties which the introduction of the quantum of action into the well-established classical theory has encountered from the outset, which have already been indicated. They have gradually increased rather than diminished, and although research in this forward march has in the meantime passed over some of them, the remaining gaps in the theory are the more disturbing to the consensus theoretical physicists.
So what's good, JK? Welcome back to our video.
Shut up, Minx. In fact, what in Bohr's theory served as the basis of laws of action consists of certain hypotheses. With the generation of laws and action consist of certain hypotheses which generation ago would doubtless have been flatly rejected by every physicist. That with the atom, certain quantized orbits, i.e. picked out on the quantum principle, should play a special role, could well be granted. Somewhat less easy to accept is a further assumption that the electrons moving on these circular curvilinear orbits and therefore accelerated radiate no energy, but that the sharply defined frequency of an emitted light quantum should be different from the frequency of emitting electron would be regarded by a theoretician who had grown up in the classical school as monstrous and almost inconceivable. But numbers aside, and in consequence, the tables have been turned. While originally it was a question of fitting in with as little strain as possible a new strange element into an existing system, which was generally regarded as settled, the intruder, after having won an assured position, now has assumed the offensive, and now it appears certain that it is about to blow up in the old system at some point. Hold on. The only question now is at what point and to what extent will this happen? If I may express at the present time a conjecture as to the probable outcome of this desperate struggle, everything appears to indicate that out of the classical theory that the great principles of thermodynamics will not only maintain intact their central position in quantum theory, but will perhaps even extend their influence. The significant part played in the origin of the classical thermodynamics by mental experiments is now taken over in the quantum theory by P. Ehrenfest's hypothesis of the adiabatic invariance, and just as a principle introduced by R. Clausius, that by any two states of a material system are mutually inconvertible on a suitable treatment by reversible processes form the basis for measurement of entropy, just so do the new ideas of Bohr show a way into the midst of the wonderland he has discovered. Okay, there's a few more equations coming up, just so you know. Okay, there's one particular question, the answer to which will, in my opinion, lend an elucidation of the entire problem. What happens to the energy? What happens to the energy of a light quantum after its emission? Does it pass outwards in all directions according to Huyn's wave theory, continually increasing in volume and tending towards infinite dilution, or does it, as in Newton's emanation theory, fly like a projectile in one direction only? In the formal case, the quantum would never again be in a position to concentrate its energy at a spot strongly enough to detach an electron from its atom, while in the latter case, it would be necessary to sacrifice the chief triumph of Maxwell's story, the continuity between the static and the dynamic fields, and with it the classical theory of the interference phenomena, which accounted for all their details, both alternates leading to consequences very disagreeable to the modern theoretical physicist. Whether the answer to this question, there can be no doubt that science will someday master the dilemma, and what may now appear to us unsatisfactory will appear from a higher standpoint as endowed with a particular harmony and simplicity. But until this goal is reached, the problem of the quantum of action will not cease to stimulate research, and the greater the difficulties encountered in its solution, the greater will be its significance for the broadening and deepening of our physical knowledge. Notes. The references to the literature are not claimed. 2 more pages. No, 3 more pages, sorry. In a way complete, and are intended to serve only for preliminary orientation. 1. G. Kirchhoff. Über das Verhältnis zwischen dem Emissionsvermögen und dem Absorptionsvermögen der Körper für Wärme und Licht. Gesammelte Abhandlungen, Leipzig. J. A. Barth, 1882, page 597. H. Hertz, shut up, Binks. M. D. Phys, 36, page 1889. Sitz Ber die Prus, Akkad, D. Vis, February 20, 1896, and D. Phys, 60, page 577, 1897. Sitz Ber die Prus, Akkad, D. Vis, May 18, 1899, page 455. L. Boltzmann sits there, and then there's the equations. U equals A times E negative to the power of negative B divided by T. According to Wien's law of the distribution of energy, the dependence of the energy U of the resonator upon the temperature is given by a relation of the form this equation, since 1 over T equals D squared times S over du to the power of comma to the power of prime, or prime, I guess, where S is the entropy of the resonator. We have R as used in the text. R equals
Alright, bitches, we're gonna absolutely beat you up.
Totally.
D squared times
Yes.
S
I'm gonna grab that. Are you freaking serious?
It costs money, idiot. Haha.
equals
L.
B U.
Where are we going though?
Shut up, Minx.
Moisty Myers.
According to Wien's displacement law, the energy of U of the resonator with the natural vibration period V is expressed by U equals V times F T over V. In Andy Phys 1, page 719, 1900, Allumer and Epitime Verhandel der Deutschen Physikal-Gesetz 2, page 163, 1900. H. Rubens and F. Krobel, Sitz Ber der Prus Akadewis, October 25, 1900, page 929. It follows from the experiments of H. Rubens and F. Krobel that for high temperatures, U equals CT. Then, in accordance with the method quoted in 7, R equals 1 d squared times s over
Well, yeah, Jay.
d u squared equals negative u squared over c. Put r equals 1 d squared times s over d u squared equals negative b times u minus u squared over. Are you guys playing Fortnite? See.
No,
No.
Oh.
That would be funny.
Because I
That
heard
actually
Moisty
would be
Myers.
That was a joke.
D times S over D U equals 1 B log.
I don't have a card.
I just imagine a random person just coming to the stream to learn about quantum physics,
1 plus
and then this is us.
B.
What do I call
C
the new person they call Spencer?
Yeah.
Or- Okay.
Every new person that joins the stream is now named Spencer.
I'm
Once
talking
the
about, like, in
radio,
the Discord
once
call. I'm talking about
the
the
In no
Discord
way I
call.
can actually
no.
so much drift with these cars. That's
U
crazy.
equals BC
We've also been streaming for like 4 hours already.
E to the power of negative B
Where you
divided
at,
by
Jay?
T minus
E-Mom's
1.
house.
But my mom is dead.
CF
Exactly.
Verhandlungen
What?
der Deutschen Phys. October 19th, 1900, page 202. CFW Nernst und TH Wolf. Wer die Deutsch Physges 21, page 294, 1919.
What?
For the absolute value of the energy is equal to the product of inert mass and the square of light velocity.
Where you at, Jay?
Verhandlungen der Deutschen Phys.
E-Mom's house. Yeah.
December 14, 1900. I'm almost done, guys. One more page. 237. Generally, if K be the first radiation constant, the mean kinetic energy of a gas molecule is U equals 3 over 2 times K times T. If we put therefore T equals U, then K equals 2/3. In the conventional absolute Kelvin temperature scale, however, T is defined by putting the temperature difference between boiling and freezing water equal to 100. CF, for example, L. Boltzmann, Zur Erinnerung, and Josef Loschmidt. Popular Schriften P 245, 1905. E. Rutherford and H. Geiger, Proc-Roy Sock, Aval, Proc-Roy Sock Aval,
Sock?
81.
What?
Page 162, 1908. CFRA Millikan, Phys Zaitscher, 14 P 796, 1913, 21. The evaluation of the probability of a physical state is based upon counting that finite number of equally probable special cases by which a corresponding state is realized, and in order to sharply to distinguish these cases from one another, a definite concept of each special case has been necessary to be introduced. A. Einstein and D. Phys. 17, page 132, 1905. A. Einstein and D. Phys. 22, page 180, 1907. M. Born and Th. V. Carmen Phys. Zetcher, 14, P. 15, 1913. B. P. Debbie and D. Phys. 39, P. 789, 1912. W. Nernst, physical.
Matrix, what you doing?
Zeitscher. 13. Shut up, Minx. P. 1064, 1912. A. Eugen Sitz Bear D. Prus Akkad D. Wis. Page 141, 1912. O. Sacker and D. Phys. 36, page 958, 1911. H. Tetrode Proc. Akkad. What?
1911? Like the pistol?
Is that the end of the reading?
Sorry, my dad interrupted the reading. Anyways, PW. Where was I?
Jay? Where are you?
Osaka
What?
and
Oh,
Defizz.
Your mom's
36
house.
page, 958, 1911. 29. H. Tetrode Brock at Akkad Sai, Amsterdam, February 27, March 27, 1915. My dad's really rude for interrupting the book, honestly.
Real.
He should go die. Anyways, H. Tetrode Brock at, I already read that. J. Frank and G. Hertz, D. Deutsch, Physical Gesture, Jess, 16, page 512, 1914, 31. P.H. Leonard and Defizz, 8.
The question
page
is, where are you,
149,
Matrix?
1902. E. Ladenburg,
Nowhere.
D. Deutschen,
Really?
Guess, 9. P. 504, 1907. R. A. Milliken, Phys. Zeitcher, 17, page 217, 1916, 34. E. Warburg, Uber den Energiemasatz, my Photochemischen, Vorganen and Gassen, Sinsberg de Proust, Akkad de Wyss from 1911 onwards. Enbor Phil Mag 30. P. 394, 1915. A. Summerfield and Defizz, 51. pp 125, 1916. F. Passion and Defizz, 50, page 901, 1916. P. Epstein and Defizz, 50, p. 489, 1916. P.W. Phys.
Are we done?
18, p. 276, 1917. E. Wagner and Defizz, 57, page 467, 1918. P. Ehrenfest and DP. We finally made it to part 3, guys. Thank you for watching the stream today. Go sub if you haven't. And also, I am going to eat dinner.
Loves Jay.
Also, we'll be doing 6 parts of the stream, apparently, or like 6 to 9.
With
Nice.
the Matrix.
Yeah.
I've
And
waited
also,
for so long to
Minx
play that
needs
clapping noise.
Minx needs to stop interrupting us. Anyways, I will see you guys probably tomorrow. I will do it.
Yeah.